Professor Law, I think you can start the
You
introduction.
can start.
Thank you.
Okay. So we are very much privileged to have Professor Tianfeng Lu to come here to give us a couple of days of seminar with mechanism model reduction and advanced chemistry solvers. That I always like to, when introduction, I like to tell some stories just for fun. That you know, my introduction to complex chemistry is torturous. The long time. You know, I was trained. I graduated from Professor Williams, and he's a great theoretician, and I was brought up as doing everything with one-step chemistry. So for the longest time, I was very happy with one-step chemistry. I remember once I was chatting with Professor Sevashinsky, some of you know, and then we both felt very happy that the one-step chemistry can explain everything. That we felt good. But then later we realized, I came to realize that there are things you just cannot. And then eventually, certain time, probably in the mid 80s, I have a student that's Professor Igofopoulos. You guys probably know he's now the editor-in-chief of Combustion and Flame. And he started doing complex chemistry, and he showed me, say, Professor Law, I can do all this, and they agree with my experiment, measure the flame speed. Oh, that's interesting. So I started getting a respect for complex chemistry. And then, of course, it gets real complicated, right? And then one needs to go into the mathematics to do that. Then I also remember that in the late 80s, Professor Harvey Lamb came to visit me. That time I was at UC Davis, and Professor Lamb came, that time he just started working on CSP, computation with singular perturbation. So he gave a seminar. And then that's where, you know, well, people have been working on the mathematics in analyzing complex reactions, but then that really opened my eyes. Mathematics can really do wonders to this complex chemistry. And then later, moving forward faster, and then I had the great fortune to have Professor Lu in my group, and out of his own initiative, totally, he developed the directed relation graph theory. It is really a breakthrough concept to do that. And later, one thing or another, he kept on working on different aspects of mathematics. Then the CIMA, right, computational CEMA, CIMA. So he is, by all measures, a leader in the mathematics of looking to chemically reacting flows. So in the chemistry of that. So again, it's I should now leave the podium to him. We are fortunate to have him to give us a 2 days lecture on these aspects, and I just leave it to you, Professor Lu, and the audience is yours. And again, thank you very much for taking the time to give us the seminar.
Thank you, Professor Law. I learn something new every time, every single time. Something interesting about what happens in the 1980s, 1970s, maybe even. So
yeah,
a lot of new stories.
I have many stories. Many stories.
every time I learn something new.
Yeah, my children been telling me on Father's Day, they say, Daddy, you should write a book. Not the text, not the technical book, but the stories. I have a lot of stories to tell you guys. Okay, anyway.
So yeah, so my topic today is the mechanism model reduction. So we'll be focused on model reduction today. And tomorrow, maybe it's the remaining part for model reduction, and also some chemistry solver stuff. And my story starts from much later, right? You all know, in the early 90s, I came to Professor Law's lab. So shortly afterward, I started this project on chemical kinetics and model reduction. So you can imagine 20 years ago, Professor Law's vision, the importance for reduced models. It's quite something if you think back. Today, it's almost routine. People get reduced models, detailed kinetics, they compile it through all different experiments and computation, and they put together hadron reduction. So because there are so many detailed models developed, you have to go through reduction to make sure it can be efficient and also retains good accuracy when you apply them in this time-consuming CFD simulations. Today, there's really like a daily need for people to use reduced models. So if you pick up a job like developing reduced chemistry, that's quite a good job actually. It will keep you busy. So early in my days when I start just developing these methodologies for model reduction, there's a story for me. So I never told other people, you know, how did I feel when I started this work. So one word I can describe is somehow clueless. Okay? Clueless. From the beginning, you really don't know much about what's in the chemical kinetics. So what stuff do you need to care about? Right? What's important? What's not important? So many things there. As a fresh PhD, how can you know how to do it? Like, so my starting point is that I have a Visual Studio, like a programming tool, right? I have a Fortran compiler, have a C compiler. So I have been a programmer before for quite a while. My interest was computer programming and also some kind of computing method algorithms. And that's what I had. Actually, how did I start? I just started from what I had. Sounds to be some kind of awkward, but that's what happened. Okay, and then I started writing programs. I really have no clue what should you do to actually make everything work well without surprise. If you get a reduced model, so people run simulation with your model and they don't get a garbage, right? So that's some kind of quite high pressure. If you give people bad reduced model, so someday they tell you, I run like a 2 million CPU hour simulation, I get a garbage. So that's all your fault. it drives you crazy. So it's a lot of pressure in the beginning. So in the beginning, it was not pleasant, and you have to work around to see, scratch your head, see what can I do. So the first thing I do is to read the chemical package, read through all the sticky leaf subroutines to get some kind of flavor, and what these subroutines are doing. You learn what people did before, all the software stuff, all the methodology, the theories behind. It took many years for me to get familiar with the environment or the toolbox. At that same time, I've been thinking of different ways. You can try this, you can try that. In a lot of cases, people have the ideas, say you want to develop a method because it's derived from top down. You have some crazy idea, and then someday you sit down, you derive like 20 pages equations, so then next week you come up with a working method. It's never the case for me. For me, it's always error and trial, the trial and error. So you try this to see if it works. It doesn't work, you have to try something else. Somehow it has always been like this for the last 20 years for me to do model reduction. Despite we have this different method developed, right, for skeletal reduction, for timescale based reduction, so which I would talk next. But the overall feeling is for the model reduction, you're dealing with very complicated stuff. And in the beginning, you really don't have a lot of clues, and you can just routinely go through something to get a working result or working method. You do need to try a lot of things and to learn at the same time you work. So that's what happens. And eventually, till now, because last you probably still remember a few years ago when I gave the summer school lecture, I was trying to present it in a manner like all the methodologies are trying to be rigorous, derived, everything working just without a surprise. But then later, when I think more, actually I realize more about this model reduction business is more about a trial and error. You learn while you work. Okay, so you probably will find similar experience if you work on this area, or if you work on chemistry, work on overall combustion problems. The combustion problems, in my opinion, are really the most difficult problems you can probably find in engineering. Let's see, it's really difficult. A lot of things we don't fully understand. We are still learning, so everybody is still learning here. So it's totally all right. We don't have like a 100% clear clue to do research. So iteratively we can learn things new and to learn what's not good in our method, what's good in our method, and to do improvement. So therefore, today I will just try not to throw all this method as if they are rigorous working method. Let's never give you surprises. So if you think model reduction, what is model reduction? Actually, model reduction is to derive some experience. You can call it a reduced model. Okay, concentrated information from something very complex. You can call it a detailed model or detailed mechanism. And this detailed stuff is highly nonlinear. Overall, you can call the whole rules governing the world is like a detailed model. And you derive a subset of information from this. You learn something from this. And then what you want to do is you want to use this experience to solve some new problems. And we know, based on our daily experience, you can never guarantee whatever you learn from this environment or this problem will always work for new problems, okay? Sometimes the experience work well for many problems. Sometimes it doesn't work that well. And similarly, if we develop methodologies for model reduction, we have similar issue, okay? So basically we're deriving information, concentrating information from a larger system and try to use it to predict some new stuff. Nobody can guarantee it always work. So a lot of people have been asking this question. Well, reduced model, can you guarantee it work for new problems? Short answer is no, okay? But if short answer is no, then what's the point to work on model reduction? So there are still a lot of good points to work on. It's just like doing any engineering work. So a lot of cases we don't deal with perfect routines. Okay? In computer science, many cases you get a 100% perfect algorithm. But in this nonlinear world, a lot of cases we have to live with approximations, limitations, and this identification of subdomain of interest, things like this. Okay, and we don't have perfect methods or perfect routines. Otherwise, we probably won't call it research. It's like if you have perfect stuff, you could call it linear algebra or some kind of computer algorithm. It could never give you a surprise. So for model reduction, we get surprises. But some experience are better. It can save you effort, make her work more efficient. Some are probably not that good. It makes you do more iterations, less efficient, and sometimes tend to give you larger errors. So there are indeed differences between different methods, different theories, to what you use to solve different cases. So this lecture, I would try to focus on what aspects actually can make your experience a little bit better, and what scenarios and why what is the reason sometimes this method doesn't work that well. Okay, hopefully after this lecture you can get a flavor like what is the issues you have to face in each of the current methodologies we have. Even though some methods are frequently used, people think it's quite established already, but still there are a lot of issues. Okay, let me move on. So the outline of this lecture. So first of all, is the introduction. So I already give you a lot of introduction here. So I want to talk a little bit more about detailed chemistry and reduced chemistry, and then why do we need it? And there's a lot of interesting issues here we want to look into. And the second part will be the methodologies for model reduction. And what is the tricky things? What the tricky things we need? So what makes the method more efficient or tends to give you better accuracy, and what logical stuff or what theoretical stuff, mathematical stuff can give you troubles in many cases. So we try to do a better job in the future, okay? And the third part, of course, mostly is tomorrow, is some chemistry solvers. For chemistry solver, it should be a little bit different thing. When we talk about the chemistry solver or ODE solver, we try to make it more rigorous. So to develop solvers, it's a little bit different from developing reduced models. So reduced models, no matter what method you use, as long as you do validation, test the model, it works, you get a working model, okay? The methodology doesn't matter that much. You can have a good method, you can have a bad method, you can both give you a model. If the model you are not happy with it, just go to redo it. So with a fair or even poor method, you can still get a reduced model if you do enough iteration and refinement. But for solver, it's a different story. You don't want to get surprises from solvers, right? If you run CFD, sometimes solver give you wrong results. You will not be happy with it. So you want something to be trustable for solvers. So the requirements for model reduction method and solver method, they are very different in this aspect. So we'll talk about what the tricky stuff for solvers, the current solvers, and maybe the recent solver we're working on. Okay, so this two major stuff we will be talking today. So as always, in this class, I talk about the need for real chemistry. So in old days, people talk about one-step chemistry, and Professor Law mentioned in the 60s, 70s, people are happy with one-step chemistry. Right? Even earlier, actually, if you think, people develop rockets in rocket applications, and even earlier, right, in the 50s, 60s. The development for rockets are quite successful without the use of detailed chemistry. And people assume not even one-step chemistry. They assume the mix is react. Basically, when you mix fuel with oxygen, you get a product. It's like an equilibrium problem, right? So you assume zero-step chemistry, you can still solve the quite seemingly difficult problems in rocket applications. Many years, people just don't need to use very complicated stuff. But what cases and why do you need to use detailed chemistry? So later, then what happens is people look at, for example, give you two examples here. You all saw this in combustion textbooks, right? The first one is hydrogen explosion limit. So this one, the hydrogen. So the hydrogen explosion limit. So this is a canonical application showing you do need radicals and chain reaction mechanism to describe this non-monotonic behavior for the three explosion limits. And then for this explosion limit, particular second limit is chemistry limit. So it's computation between chain branching reaction and chain combination reaction involving H plus O2, right? What it goes to. So basically, this computation give you this non-monotonic behavior for hydrogen explosion. And when people realize this, actually, a lot of things in combustion, very strange flame behaviors are explained quite well with chain mechanisms. And then, today, everybody, you need to use IC engines, internal combustion engines, in cars, trucks, right, and other vehicles. So basically, for IC engines, you all know how it works, particularly for diesel engine. For the diesel engine, you have a cylinder, right? You compress the cylinder, and then after compression, temperature is high, pressure is high, right? Then you discharge, inject fuel into the compressed air, and it will ignite. So this is so-called compression ignition cases. Compression ignition, the one important thing is time. So basically, when you want combustion to happen, because when combustion happens, you can get a fast or rapid heat release. Sometimes they even give you explosion or detonation, and you want to control when it happens. And when this happens for ignition controlled engine, so there's something called ignition delay time. You're all very familiar with ignition delay time, right? And different fuels give you very different behaviors for ignition delay time. For example, for small hydrocarbons, you get this kind of straight line-like behaviors, small hydrocarbons. For a higher hydrocarbon with transportation field, large hydrocarbon fields, you get this NTC behavior, negative temperature coefficient behavior. And so this one tells you if temperature increase, your ignition delay time can be longer. So that sounds to be counterintuitive, but then later people figured out it's also due to the competition between chain branching and chain reaction. But it's different pathway from this one. Okay, it's basically oxygen addition to large molecules. Different groups of reactions compete with each other, give you this kind of unexpected behavior. So to predict a complex phenomenon in different combustion applications, particularly if timing or the rates or dynamics are important for you, you do have to figure out what happens during the process. And then the finite rate chemistry kicks in. It comes into the picture. You have to make sure the heat release rate is correct. Okay, heat release rate, or before heat release rate, we all know there's something called a radical pool buildup. So for chain mechanism, we do need radicals to build up, right? So therefore, people put all things together. Eventually, you can imagine if you get a large molecule, and then if it breaks somewhere, it form a radical, and it can give you small pieces, right? They break down into 2 pieces, 3 pieces, and to form intermediate. And the intermediate can break down again to form more intermediates. So if you get a large molecule, all the different combinations will give you many intermediate species. And each intermediate species can react with other species pairwise to give you a lot of reactions to worry about. So therefore, if you do consider all the detailed kinetic processes, the chemistry can become very complex. Okay, if you look at this diagram, this graph, this funny thing is this graph has a great background, interesting, but you can still see clearly this one on the screen, right? So this one was a statistical plot for many of the reaction mechanisms I can find, download from website. Basically, I look at the mechanism for methane, for hydrogen, for ethylene, for heptane, dodecane, whatever, diesel, biodiesels. I don't put all of them together. So many years ago when we wrote this review paper, you will find I plotted the number of reaction versus number of species here, both in log scale. Okay, and this so this point and these 2 points are what I added later after the paper was published. So before the paper was published, so basically everything is fall nicely along this diagonal line here. The diagonal line, look at the slope, was 1. The slope is 1. So basically that means on log plot, if you get slope 1, that means the number of reactions is linearly dependent on number of species. So I is a linear function of number of species. That sounds to be a very interesting idea, right? So, but I thought it for a long time. I couldn't figure out why number of reactions must be a linear function, number of species. There must be some reason. And many years after the publication of this paper, I didn't find an exception until I found Renzi's work. Because Renzi has 2 versions of mechanism, which give you much larger number of reactions, the number of species predicted by this line. Okay, and this year, or last year, actually found another one from Bill Green at MIT. So they are having a new methodology to automatically generate reaction mechanism. Okay, so if you think how this mechanism should be produced by computer, you can think each reaction of each species can always react with another species. That means you randomly pick a pair of species from the pool, and you collide with them each other. So because of Boltzmann theories, you know, there are always possibility that accretion can be fast enough or strong enough to break the bond, right? To give you some kind of a product. So therefore, theoretically, for each pair of reaction, you can always get a reaction. Each pair of species, you can always get a reaction. Theoretically, the possible reactions you can come up with let's see, number of k of species. It should be k squared, right? That's what I have been suspecting this k squared for a long time. Just couldn't find real cases until I got this point. So I connect this dot. Eventually, you find this almost slope of 2. So that means number of reactions for these guys are a quadratic function of a number of species. So what's the reason? What's the reason? So I found a little bit more. And this is the first time I talk about this. Okay. So in reality, if you consider all the possibilities, it should be this line. So in nature, each pair of species can collide. Okay. How many pairs can you pick up? It's pretty much half k squared, right? This is how many reactions you can conduct by pairing species. But each reaction can give you several possible products. So therefore, it should on average multiply by some kind of constant coefficient. So number of I should be proportional to this in the worst case. And indeed, if you use computer to automatically generate, you will get this number of reactions. This huge number of reactions. You can see for this Dodecan mechanism, it has about 2,000 species, but then it has more than 100,000 reactions going on. So almost crashed my computer. So thanks to the new technology, I have a computer, desktop computer, which can handle zero D simulation for this mechanism, and can get a reduced model for it. But then, so why all the previous years, we get this linear trend? What's the reason? So now I think I get an answer. Because people are doing model reduction. Okay, in old days, when people compile detailed model, they are doing the reduction at the time they are compiling it. So they estimate whether this reaction can be important or not. If it's not important, if they think it's not important, they probably don't bother to add it at all. Okay, so the stiff selection process naturally give you a reduced model. Except some species are still redundant. Okay, so you can just manually, it's difficult to get rid of the unimportant species. But some reactions you can easily rule out by the rule of thumb. You know, in detailed chemistry, we see we have a stable species. We call it a major species, right? And we have radicals. So therefore, some reaction involve a stable species collided with stable species. You get if you get an A plus, if you get A plus B, both like a stable species, this reaction cannot be fast. Why? Because you get high activation energy. Both molecules are strong, right? So the collision to break it is difficult. You don't get a lot of chance to break this strong molecule. So this reaction must be slow. Therefore, if you look at our detailed model, very rarely you can see these two stable molecules collide to give you a product. Another scenario is if you get 2 radical 1 plus radical 2. These 2 radicals supposedly react fast, right? But then if you get 2 radicals, they are both in low concentration. Radicals are in low concentration. If you have 2 species both in low concentration, their chance for collision is also low. And therefore their reaction rate typically is low. You don't have a lot of radical collide with radical, although sometimes at high pressure you consider some of them. Okay, but in general, most of the radical collisions are not that important. So the important ones are the A plus R. If you get a major species of radical, and this one give you, why this reaction is important? Because you get a 1 species with high concentration, right? And the other guy, this R, the radical major responsibility is to lower the activation energy. If you have radical in the reaction, your activation energy is low, sometimes even 0, okay? If you have a 0 activation energy, each collision will give you product. So the reaction occurs almost at every collision. In that case, you get a fast reaction, or it's faster than both cases, this case and that case. So therefore, the majority of the reactions are major species collided with radicals. So there are rules like this. People look at activation energy and concentration, the nature of the different species. They can easily rule out a lot of unimportant reactions. In that case, when you compile the detailed chemistry, it's already reduced. Okay. In this sense, the majority of the detailed chemistry we're dealing with are already reduced, or we call it heavily reduced. Okay. We just need to further reduce it to make it like as small as possible. So that it need more systematic method. Like if you want to do a job, you need a so-called professional model reduction worker, right? It's like people like us. So that's neat. Like if you want to use this transportation field in a simulation, 2,000 or 1,000 species, that's still too many. So we want to reduce it to 100. Sometimes to a lot of people say 10. And we know it's not possible to reduce to 10 almost. Right? So how about 100? So 100 is not easy either. So therefore we develop a lot of we call it very advanced methodologies, just to make work a lot easier for us. So you can quickly get a reduced model rather than keep trying for 200 years to get a reduced model. So we can get today, we get about a reduced model in 2-3 days. And validation, it takes about a week or 2 weeks. So overall, the turnaround time, if you have a good tool for reduction, you can finish the reduced model in about 1 week or 2 weeks. So that's pretty good, and then you can make good living with this. Okay. So now next, let's talk about how to do the model reduction. Again, we get all different methodologies. Like what's the important in the reduction, and what should we focus on, and what tools should we use? Because we have so many options to use. So what tools are very useful, or at least we found it useful for the model reduction work? So to answer this question, we need to actually start a little bit to go back to the law of mass action. So how reaction happens, right? So if you put all the different speeds together, you know, this typical, if you write as a one step or several steps, global reactions, semi-global reactions, that's what it look like with some coefficient, some species, and react with something else to form a lot of products. And then if you can somehow compute with the reaction rate, omega, and you can put in your formula. So for example, if you next page I will show you, you put all the reactions together, so what will happen? But for elementary reactions, so typically the law of mass action says there must be some temperature dependent part, okay, called reaction rate coefficient, and then it times the concentration for each different reactants raised to their stoichiometric coefficients. So you get this so-called formula, and this formula typically K is in the Arrhenius formula. Arrhenius formula says K is equal to A times T to the N, E exponential negative E over RT. So we are all terribly familiar with this formula, right? And this is heart of the chemistry. 3 parameters for each reaction, A, N, and E. So when you put all these different reactions together, so you get a whole lot of parameters to determine. So if you get 10,000 reactions, you get at least 3,000 parameters to determine. So that's a lot of work. Okay, so people use, for example, quantum computing, a lot of group theories. Sometimes you use experiments to calibrate it, try to determine all these rate parameters. So once all the rate parameters are determined, so you put all these numbers together, it gives you a mechanism file. You can put it in a certain format, for example, in chemical format. So typically today we use chemical, and sometimes we use Cantera. That's the popular packages. So we can write detailed chemistry into, right? So once you have this one, all the packages will provide you subroutines to, if you give the concentration for the different species, it speed out the reaction rates for each reaction. Okay, and all the reaction you put together, so you can compute. You can put in a governing equation, something like this. This governing equation is needed for whether it's CFD reactor, 1D flames, or CFD simulations. It's all written in the transport equation in general. Okay, so D, whatever quantity you have over DT, is some kind of a reaction term plus mixing term, whatever. So overall, this governing equation is simple, but kinetics take care of the reaction source term. It requires input of concentration, temperature, pressure, concentration, and give you reaction rates. So that's what chemistry does. So the reduced model need to identify a subset of species and a subset of reactions. But for the retained species, whatever you speed out for the reaction rate need to be correct for that retained species, and that's target. Okay, and then if you use this to simulate whether it's ignition delay time or flame speed or whatever turbulent flame, at least the remaining species equations are close to the original equation. So the solution you would expect solution would not be too far away from the detailed model. Okay, so that's the whole point for the model reduction. Now, so here comes the first key question for model reduction. Is how do we reduce the model? For example, if you get a detailed chemistry, how do you reduce it? So there are two things: species and reaction, right? We want to reduce number of species, reduce number of reactions. We can throw them away. If you want to throw them away, you have to be able to identify the important species. Which one is important? Which one is not important? Okay, you want to throw away these unimportant ones. For example, if you throw away one reaction, it give you a little error to everybody else. Why don't just get rid of it? And that's basically the idea for something called a skeletal reduction, which I'll talk in more detail shortly. Okay. Oh, by the way, today's I forgot to mention in the beginning. So how you ask questions? If you are listening, if you have questions, so I happen to have my moderator sitting beside me, so he can just read your question to me, and I can just answer your questions. So in this way, we can have some kind of almost real-time interaction. So therefore, if you get any questions about whatever we're doing here, feel free to ask questions real time. Okay. Yeah. So to identify important or unimportant species, so what do we need? If we go back to this, so for example, if we want to find if reaction is important or not, so if reaction rate is small or negligible, sometimes it's not important. So we want to look at reaction rates, for example. But reaction rates involve what? Involve species concentration. So you do need species information to identify who is important, who is not important, right? So where the species information should be from? So you can't just do random numbers. If you assign random numbers to species concentrations, first of all, your reduced model will be probably good, but it will be overkill, because many of the combinations you gave by random guessing, it won't be similar or close to what happens in real combustion systems. So we want to get a so-called something called low-dimensional manifold. Low-dimensional manifold, it means for combustion systems, the variables, it don't scatter randomly. It just scatters under some low-dimensional space. So there's some correlation between species. We want to take care of this low-dimensional quantity, low-dimensional nature for combustion problem. In this way, we can get rid of as many species as possible. Okay, so therefore, the first thing we need for any reduction is to get reasonable concentrations. The concentrations, there's really no way to directly guess them. So far, I don't think anybody can reasonably guess what concentrations you should have. So almost always we need to do something so-called sampling. Okay, we run 0D or 1D simulation. Sometimes you can sample even from more complex flames, but you need to sample the reaction states or species concentration, temperature, pressure from real flames, because what happens in real flame is what we should use to just give you maximum amount of reduction. Okay, so sampling, then here comes the question. So what systems should we sample from? Should we, if we want to use this reduced model for turbulent flame, should we only sample from turbulent flames? But then if you think a little bit further, you see we can't really do it, right? Because the whole purpose for using a reduced model is to save cost. And you cannot afford using detailed chemistry in turbulent flame simulation. How can you just run it with detailed manual first and then do the sampling? So you don't have the data to sample from turbulent flame. So you have to do some compromise. You have to compromise to use simpler flames and to get a reduced model from 0D or 1D flames. And then you still want to use this experience in more complex flames. That's basically a stretch experience. at what I mentioned in the beginning. We are trying to learn something from simple routines. Okay? We want to use this experience for some more complex problems, and that's nature for model reduction. And it's quite ambitious. In this sense, there's never a rigorous methodology for model reduction. Okay, so nothing can guarantee you that you derive a model from simpler flame and you use it for turbulent flames, it will always work. So sometimes it works, sometimes it doesn't work. But if something doesn't work, it's not the end of the world. We can always look at it and see what happened, and we learn from it, and we can do refinement. So don't be scared if you have a model, somebody use your reduced model and give you, sometimes they tell you, I got a wrong result. So 20 years ago, if somebody told me using my model get a wrong result, I would be very nervous, feel very guilty. But today, I probably feel a lot better. Okay, so for you, the same. So if you want to use reduced model, so people need to have the idea that if you choose to use any reduced model, there's a risk of using it. Okay, so there's never a risk-free CFD using reduced model. But what makes difference is if you get a very carefully reduced model, you get a good chance. In most cases, it works for many flames you play with. Okay, but if you do a very sloppy reduction, sometimes you can get a lot of surprises. So the chance of failed prediction can be frequent. So that makes a lot of difference. In other words, if you're a good learner, you carefully get your experience, you do things better than other people. Okay, if you're not careful enough, you learn something not good, and you try to do good new work, you probably will fail more frequently than those good learners. So same thing for reduction. Okay, now so now let's look at like so what system should we use for sampling? So before I start doing reduction, basically people use a lot of ignition application, autoignition. See, sometimes 1D flames. Okay, nobody really used 2D flames 20 years ago. So because we can't afford solving for it. Okay, and then some of the researchers use stirred reactors. So in the beginning, I don't actually really get the idea what's so different about the autoignition and stirred reactor. They're all combustion systems, right? And why they're so if I only use autoignition, would that be fine? Or if I only use PSR stirred reactor, would that be fine? Or if I use both, can I get a better model? These questions actually I start to have some idea about it. So I was lucky. I used both in the beginning. But if I only use one, probably today I will have a lot bigger trouble because a lot of people will be complaining about my model. So I will explain why you need actually both applications to get a quite robust and a comprehensive reduced model. Okay, and you can use 1D flames, but 1D flame can be much or largely covered by the reaction state you sample from stirred reactor. So basically, ignition and stirred reactor are two very important applications. I always use both in my model reduction. So I'll tell you the reason why. But again, this is for most cases I study. Okay? But for some rare cases, for example, if you only focus on ignition applications, you feel free to only use ignition as sample space. And if you use the reduced model for other applications, probably you will need to add stirred reactor. Okay, so now let's look at it a little bit in detail. See what's the major difference. What's the major difference between these two applications? Actually, compare with whether reduction method is rigorous or not. In my opinion, whether you choose good application to sample from, it makes better or makes larger impact on the quality of the reduced model. It's more important. Okay, so using ignition and PSR is very, very important. So ignition, what is ignition? If you look at ignition, you know, ignition, you first mix fuel and air. Okay, you suddenly heat it to some temperature, for example, 1000 Kelvin or 1500 Kelvin, 2000 Kelvin. So some kind of high temperature, but not terribly high. And then the mixture starts to cook, right? After a long time, similarly, there's nothing happened over this time. And then suddenly you see a step function temperature rise and reaches burn stage. It's almost like step function in many cases. That's typical ignition process. And this time we call it ignition delay time, IDT. And ignition delay time is one of the primary targets of combustion research. And probably half or more than half of the community is studying ignition delay with shock tubes, with rapid compression machines, with flow reactors, sometimes with jet stir reactors, with 4 major things. Okay, sometimes people design even like other applications to study ignition delay with the extraction. But the whole thing is still about ignition. So what happens at ignition is ignition has 2 stages. So this is stage one, the first stage. Second stage is here. Okay, what happens in the first stage? Temperature is almost constant, but something's going on there. We know what happened is radical is building up exponentially. So in the beginning, you have very few radicals here. So like for example, if you look at H concentration in the beginning, its concentration is very, very low. But then through some chain initiation, it starts to their slope in log scale. It grows exponentially as time. So the radical pool need to be strong enough before fast reaction can occur. So this ignition delay time, what happens is you are building up radicals. Okay, primarily, for example, H plus O2 go to OH plus O. That's one of the most important reaction for all different fuels, all hydrocarbon fuel, and also for hydrogen. Okay, so this is probably the most important radical branching pathway everybody need to go through. So after a while, when you have high enough concentrations for radical, and then this thing can happen. This is called a thermal runaway. What happens is it starts to form to form product. For example, water. Okay, how do you form water? You have, for example, H or whatever fuel plus OH radical. If you get an OH, you get a water. Let me see. H2O plus H, right? So you get a lot of heat release from forming forming product, but you have to have high enough radical concentration for this formation of product to be significant or to be important to see anything. Okay, so therefore, so this is so-called fast thermal runaway. So what happens thermal runaway is mostly ignition delay time. People don't care what happened there because it's like a blink of an eye. Nobody can truly resolve what happens during thermal runaway. So we can just treat it as a step function. So we measure ignition delay time, basically tell you how much time it takes to build up the radical pool, right? So that's the whole story. So a lot of the experiments or kinetic study today is focused on making the time scale for radical pool build up to be correct, or to make ignition delay time correct. Now, why this is so important for many engineering applications? For example, for IC engines, you need to do the timing, right? You don't want the ignition to happen before you want it. Like in spark ignition engines, you compress premixed gasoline and air mixture. You don't want autoignition happens before spark is fired, because then you get an explosion. That's called knocking, right? If you get knocked in your engine, that's the explosion, can damage your engine. So you want to control the ignition delay time. So if you want to predict ignition delay time, depend on different working conditions, different mixture conditions, you have to have a chemistry to predict the radical pool build up time scale correct. And that's a lot of effort people spend on. But if you think the radical pool time, this time, IDT, compare with how much time it takes for the thermal runaway to happen, the ignition delay time is dominated by the radical pool build up. Okay, so thermal runaway, if you make the time scale off by factor 2, 3, or even 10, it doesn't really matter much. Your IDT is still perfect. Okay, so that's why a lot of cases you see, for now, people say this reaction is the best understood reaction. So H plus O2 reaction is the best understood reaction in chemistry world. Okay, its uncertainty goes, let's see, about 10%. So that's the kind of conservative estimate. Okay, all the other reactions, like heat release reactions, for example, the answer can be a factor of 2, factor of 3, or factor of 5, or sometimes even order of magnitude. But it doesn't matter too much, because if you this step function is a little bit faster, a little bit slow, it really doesn't matter too much for your compression ignition problem, right? As long as you can get your timing for ignition correctly. Therefore, for this application, it's okay. If as long as you get your ignition condition, means if you can build up your radical pull correctly on time, then you're fine with your simulation. So there, if you look at the literature, a lot of people only use autoignition to get reduced model for IC engine applications. Sometimes it makes a lot of sense. Just keep in mind, if you only use this reduced model to predict ignition timing, then you're fine. But some cases, if you are dealing with how fast heat release comes into play a role here, then you'll get into trouble. If you don't resolve the heat release rate correctly, your reduced model will give you trouble. For example, if there's one more thing, because one more thing I want to emphasize for ignition problem is that for small molecules, it's H radical buildup. Okay? But if you get a higher radical for large engine fuels, you get a so-called two-stage ignition. Okay, the first stage ignition delay, people call it the ignition delay time for the first ignition stage, is controlled by the so-called O2 addition to the fuel molecules. As we said, it's a different reaction pathway giving you the NTCB here. Okay, and the second stage involving the H radical buildup. Okay, so it's different reaction pathways. So you need to predict both correctly. So both pathways correctly. If you start your engine from lower temperature, okay, from 750 Kelvin or 800 Kelvin, 900 Kelvin, so that's pretty much located in the so-called NTC regime. This regime, you do need to worry about 2 stages, okay? But if you somehow have your engine start from a higher temperature, for example, you get a much higher compression ratio, you start from above 1000 Kelvin, so typically in that case, you don't have 2 stages, you only get 1 stage. So as long as you can capture this build-up for each radical pull correctly, so then your ignition didn't have to be fine, okay? So therefore, some engines involving low temperature chemistry, so your reduced model will be a lot more complicated because you need to consider this additional reaction pathways. Some high temperature ignition is above 1000 Kelvin, typically. Then you just need to capture one reaction pathway or one group of reaction pathway, make sure it's correctly in your reduced model. In that case, you can predict your ignition time correctly also. Okay, but overall, for both cases, you don't need to worry too much about the heat release rate. Okay, and if you compare both the small, this is a method here. Okay, this is a happening. So basically, we're comparing small molecule versus engine fuel. For small molecules, you see if you plot the ignition delay time versus 1 over temperature. Okay, ignition delay time, 1 over temperature. What do you see is for small molecules, you get almost like straight lines like this. But for higher molecules, you get this NTCB here. It turns back. We all know for this plot of ignition delay time versus 1 over T, the slope gives you the activation energy. All right. Why is that? Because ignition delay time, tau, is inversely proportional to reaction rate. Right? If you reaction faster, it takes less time for ignition to happen. Right? It's linearly inverse. It's inversely proportional to this. And if you take the log, you take log. No, log here, sorry. You get negative log omega. Okay, omega, because you get an exponential of negative E, exponential of negative E over RT. If you take the log of this, so this one will give you E over RT. Okay, therefore if you plot log tau versus log T, if you log tau versus 1 over T, your slope will be E over R. So that's how people actually determine activation energy for rate controlling reaction in the ignition processes. But for small molecules, what you can see, there's a question here. For a small molecule, you can see the slope. You get a 1 slope. Okay? So that means there's one single reaction controlling the ignition delay time. And that's pretty much has something to do with H branching. Okay, but for larger molecules, you cannot have one activation energy to control everything. You get one slope here, two slope here, another slope here. At least 3 different effective activation energies. So intrinsically, this NTC behavior, there's no way you can use one reaction, one step reaction. There's no way you can capture this behavior. Okay, because activation energy are changing at different temperature. Okay, so this tells you how tricky this chemistry can be, even for ignition chemistry. Okay, what's the question here? Can you read the question?
Yeah. So a question from Tarish Tanija. Will getting an accurate thermal runaway time matter for flame stabilization or cases which can have rapid extinction and reignition?
I will talk about this rapid thermal runaway next. Okay, yeah, that's a good question. So let's go next and to talk about this stuff. The next stuff is about a stir reactor. Okay, so why did we need to talk? So I happen to use stir reactor. In the early days, 20 years ago, I started working on reduced model. I didn't really know why I should use PSR to do my sampling. I just happened to include it. Luckily, I use it in my work. And by the way, this is the first time I confessed. Okay, previously it's all the sound like as if I'm so good to know I use ignition delay and PSR in my model reduction. But in the beginning, I really didn't figure it out. But I just luckily get PSR in my sample space. But it turned out to be working well. And after many years, I finally realized why PSR is so important for flames, particularly turbulent flames. Okay, why? Let's look at a PSR. You know, stir reactor basically you get a reactor like this, right? And you have inlet, you have outlet. The inlet can be premixed, can be non-premixed. It doesn't really matter. You can premix. You can mix fuel and air before injecting it, or you can inject the fuel and air separately. But this perfect mixing, actually, we instantaneous mixing with the model. So basically, as long as you put air molecule into the reactor, everything will become uniform immediately. Okay, so therefore something's happening in the stir reactor. Stir reactor is something similar to the recirculation zones in a lot of things. If you imagine you have a cavity stabilized burner, or you have a jet engine combustion burner, or whatever continuous flow burner, sometimes in just industrial boilers. So the flames are there. Okay, it's continuous. It's not like a traditional ignition process. The flame is always there, and you tend to induce some kind of recirculation, or some kind of mixing to mix product, the high temperature hot product with fresh mixture. In this way, whatever comes in, the fresh mixture comes in the reactor can quickly react. Okay? And stir reactor, if you look at the equation, it's very simple. So basically, it's just so I will talk about this equation next. But then we know any continuous or steady state combustor almost always features something called S-curve. We studied from the combustion textbook, right? S-curve. It's a feature for steady state flames or continuous flow burners. You get a upper branch, middle branch, the upper branch here, middle branch here, and lower branch here. Lower branch, of course, temperature is low. It's like nothing is reacting. If you get a reactor is going on, but you don't ignite it, so fresh mixture coming in, fresh mixture goes out. So that's what happens in the lower branch. It's not interesting. Okay? What's interesting is the upper branch and the middle branch. The upper branch is basically is burning state. If you have a flame going on there, as long as you keep on pumping fuel to it, it keep on burning. So for example, you pick a flow rate. The x-axis is flow rate or inverse flow rate. People call it different things. Sometimes people call it residence time. Sometimes people call it Dunkel amount. Sometimes people call it flow rate. So it's all whatever related. Okay, with a little bit of transformation, they're all related to each other. So it's flow rate, how fast you let it flow go through. And then if you pump a lot of fuel to the mixture, to the burner, so basically you don't give enough time for the fuel to react before they exit. So you have a little bit so-called incomplete reaction. Okay, temperature goes down a little bit because you don't give enough time for the reaction to be fully equilibrated. So if you keep on increasing flow rate or reducing residence time, and eventually the temperature becomes lower and lower and reaching a turning point. And this turning point is so-called extinction point. We all know this upper turning point is called extinction point. Okay, the flame is suddenly gone and jump to lower branch at this extinction point. And the extinction point for a long time somehow is not very well understood. So what is extinction? So I try to ask people what extinction is. I get many different versions of answers. A typical answer is extinction means the flame is gone. Someone says extinction is slow reactions. Someone say extinction is whatever, like you reach minimum residence time or whatever. It's some kind of jargon that you don't really understand what it means. But different versions have, so they have different explanations for what extinction really is. So what happens in extinction is actually extinction, if you think, the reaction rate at the extinction point is not actually low. Instead, it's kind of high. Okay, I will show you some picture shortly. So contradictory to a lot of intuitive feelings, extinction point actually tells you where reaction is fastest. It's fastest reaction rate, or we call it the limit of a fast reaction. How fast chemistry can go. It's very important. So along the whole S curve, in all the state, whatever combustion system you have, the extinction state is the fastest you can get the chemistry go. Okay, it cannot be faster than this. You can push it to be to this point, but it cannot go beyond this. And that makes PSR why it's so important, because it tells you your reduced model has to be able to capture how fast chemistry can go. Okay, let me show you some evidence. Okay, this is some calculated result for hydrogen in PSR on different pressures for hydrogen. You can try for different fuels, whatever fuel, whatever. As long as you get this upper branch and middle branch, you get a turning point. Okay, so what do you do? And then you plot your heat release rate. Heat release rate. Yeah. So you transpose your coordinate. So you plot temperature versus heat release rate. Okay, heat release rate. And then what you do is you shift this for each curve. You move the turning point to the center. So basically, we shifted each turning point to the center, to the so-called center temperature. Okay, then you will find all the curves actually peak at the center, or almost exactly peak at the center. So there's no exceptions. Basically, the extinction point, the turning point of the upper branch, the upper turning point on the S curve tells you what is peak chemical reaction rate. If you want to design a burner to burn things fast, where do you think you want reaction to happen? You want it to happen here on the upper branch, or you want to happen here on the lower branch, or do you want it to happen on the turning point? So if you want to design a burner, so that's a really question, right? So if you want to find a job in Pratt & Whitney or GE, design a combustor, jet engine combustor, okay? You want to minimize the combustor and to maximize the thrust, right? That means use the smallest volume you can get to get the maximum burning rate, okay? That's your design purpose. So we all know that when temperature is higher, reaction tends to be faster, right? Why don't we just run the combustor at high temperature? If we reduce flow rate, temperature will be high, but reaction rate will be high. Now the answer is kind of straightforward, because if you think when temperature is high, you don't have a lot of fuel left. Your reactant concentration is too low. In that case, when you have KT times concentrations raised to whatever, your concentration is too low. Although this is high, this concentration is too low. So therefore, near equilibrium, if you imagine near equilibrium reaction rates go zero. Although temperature is high, reaction rate goes zero. So it's not always the case when you have high temperature, reaction rate is always high. Not the case, okay? And then you don't want to operate on a middle branch for obvious reasons, right? Because on the middle branch, temperature is low. Why temperature is low? Because you don't have a lot of burning. You have a lot of unburned fuel on the middle branch. And you don't want to just exhaust the unburned fuel. Clearly, it's not the option, right? So how about let's operate at a turning point? And at turning point, what happens then? You get the peak reaction rate. So that means for given volume, you time the reaction rate, you get the fastest heat release rate possible. It sounds fabulous, right? In reality, indeed, we are just trying to minimize the volume and try to increase the rate. So basically, we're pushing the reaction condition or the operating condition for combustor toward this peak point. But somehow we have to stop somewhere before we reach this point, because when you get to this point, your flame can quickly jump to the lower branch to extinguish. That means if you not careful, if you jump a little bit over the limit, your flame is gone. So that's what happens, so-called lean blowout in aerospace applications. So when you like where the airplane goes down, like okay, from high energy to go down, so you get a fast flow rate. You don't need to have a strong burning because it's going down. So your flow rate is high actually, and then you don't give a lot of fuel. You have very lean mixture. In that case, if your flow is a little bit over limited, too fast, it will blow off the flame, and then you will lose the flame. Once you lose the flame, what happens? You cannot easily bring it back, because once you lose the flame, if you want to bring it back, you have to go through a very painstaking process. Just take a long time, very harsh condition to bring the fire back. Okay, so therefore, once you have LBO, it's kind of stressful situation. Okay, you need to avoid operating under this extreme condition. So that's why we want to have continuous burning to happen at the peak or near the extinction condition, but we don't want it to extinguish. So we need to have some kind of safety margin. And this safety margin actually affects your performance for the burners because it limits how fast you can burn. You probably cut it off from top. You operate somewhere here, or somewhere here. Sorry, somewhere here on the high temperature part. Okay, so in that case, then you can still have reasonably fast burning, but you don't usually get extinguished or LBO or blowout. So that's the story. So now the key message here from this story is the extinction point for PSR is really, really important. And if you include the sample space from PSR, particularly those near the turning point in your sample space, your reduced model can capture the fast heat release process. And you can use your reduced model for jet engine applications, for example, and also for flame holding. So a lot of challenging aerospace applications, you can use your reduced temperature for. But if you don't use something like this, like you can use stir reactor, sometimes you can use stretch the flames. You can get a similar reaction state. But you only use autoignition, sometimes you can miss these cases. And then if that's the case, you probably can miss this peak reaction rate. And then your predicted result will be probably off by too much. And if you over predict or under predict your burner design, that's not a kind of very pleasant scenario, right? So you want to avoid that. The easiest way is just to add PSR in your sample. that's a story. So for the S curve for small molecules, it's straightforward, just like what happens in textbook. But if you want to deal with real engine fuels, and the S curve actually can be a little bit more complicated. You can have more wiggles here. It's like this for DME. DME is people call it a diesel fuel. It's for a compression ignition. It's similar to diesel fuel. Actually, a lot of higher hydrocarbon, longer alkanes will give you similar behavior. You get a cool flame behavior. For continuous flow flame, you get this kind of middle plateau, which is called a cool flame. It turns out you get a stable flame here, you get a stable flame here, you get a stable branch here. So you get this is interesting thing, just the interesting thing. So sampling from this regime depend on where you want to use your application. If you never worry about extinction for a cool flame, or your operating condition actually doesn't care too much about the existence of a cool flame, probably you don't have to deal with this. Okay, that's why for engine application, for jet engines, if you don't worry about the low temperature chemistry at all, you just throw them all together, you can still compute the engine applications, the jet engine applications quite well. The jet applications are controlled primarily by high temperature chemistry. So that's a very important message. Okay, but in some cases, if you design a cool flame burner, we don't have this burner yet. Yeah. For some reason, if you design a cool flame burner, if you want to use CFD to facilitate your design, you do need to add this. Okay, but this part probably you can also get this flavor from the first ignition stage or second ignition stage in the autoignition. So maybe, okay. But the key point is here. This regime is the fastest possible reaction rate you can have for a particular field and whatever condition, given temperature, pressure, and the equivalence ratios. So that's the fastest you can get. You want to make sure this peak reaction rate is correct in your reduced model. And the good news is it turned out only very few species and reactions are controlling this fast burning. Therefore, if you include this one, actually it doesn't make your reduced model much larger. It's probably just a few species, 2, 3, 4 species, and with 10, 20 more reactions. So it's never a big problem. You always use autoignition and PSR to derive reduced model. I never bother just to get a reduced model only using autoignition. So I always use autoignition and a stir reactor, even for applications like the IC engine people are using. Just make sure you don't mess up with heat release in case there's something important, because the risk of messing up heat release rate doesn't really worth the fuel species reduction. Okay, and for different fuels, the S curve can be very different. Okay, so if you look at this different fuels, so this green curve is hydrogen, and propane and larger hydrocarbons. When you have hydrocarbon fuels larger than ethylene, for example, from propane above, so actually whatever alkane you are using, so whether it's isoalkane or normal alkane, so although their ignition daily time can be very different, but their extinction behavior is almost the same. That's what we found in comparing different fuels. If you just superpose the S curves for different fuels, but you have to use the same mechanism. Okay? If you use, for example, Lawrence-Livermore mechanism, you compute Lawrence-Livermore mechanism for all the cases. You find whatever fuel you're using, this part, the ignition part, is almost the same, because only very few reactions and species controls this heat release. Okay, so pretty much it has something to do with CO. Okay, formaldehyde, HCl, water, H, OH. You will find this kind of small molecules like play the dominant role here. And for hydrogen, it's totally different. For hydrogen, you can clearly see there's about almost 2 orders of magnitude different here. So in log scale, seems like there's not too much difference on this plot. But if you imagine 2 orders of magnitude difference in extinction time, that means the reaction rate for hydrogen can be 2 orders of magnitude higher than hydrocarbon. So hydrogen can be much faster to react if you want to push it to the fast limit. Okay, so that's why for hydrogen, actually, when it's going to the fast reaction limit, it's very difficult to control. And once it's burned, if you want to extinguish it, it's a lot more difficult to extinguish than hydrocarbon fuels. So extinction for hydrogen is much more difficult than hydrocarbon fuel. That's the message you can derive from comparing their extinction behavior. And also, hydrogen can survive much lower temperature. For example, for this case, hydrocarbon fuel, it turns, this is high pressure case, 30 atmosphere. Okay, you find about 2,000 Kelvin hydrocarbon flames just gone. Okay, and then but hydrogen can go much lower temperature, even 1500 Kelvin, it still burns as fast as 2,000 Kelvin. So that's dramatic. Okay, so that means hydrogen is really some strange atom. It's very, very different. So 20 years ago, people do hydrogen research, try to use hydrogen as an alternative fuel, and it turned out somehow that research died down because they said there's not a natural resource for hydrogen. But if you look at the kinetics for hydrogen and the burner design or whatever, hydrogen is something interesting you can use to do a lot of things. For example, if you add a little bit of hydrogen to the hydrocarbon field, it may affect your burning limit a lot. For extinction applications, it can have a lot of impact. So you blend hydrogen in your hydrocarbon field, you can have some surprises. Okay, so that's something. I guess good news is today hydrogen research comes back, a lot of applications. But this is one possibility you can look into, to blend hydrogen into hydrocarbon field and to improve the fast burning performance or flame stabilization performance. Yes.
We have a question from Babitra. What is the relation between the extension strain rate obtained from counterflow plane and the extinction condition obtained from PSR?
They can translate to each other. So extension state for counterflow, basically you get the limit condition in the reaction zone. So if you get a non-premixed counterflow, so basically you get a fuel, you get an oxidizer, but the peak point is still here. So in the reaction zone, it acts almost like a stir reactor. You pump fuel from one side, oxygen from the other side, and then you just, because the reaction zone is so thin, the mixing is super fast. Because diffusion time scale is very short, right? Remember, diffusion time scale is thickness square over D. If you get a very thin reaction zone, when it's stretched to limit, you get a tiny, very, very thin reaction. And diffusion will quickly blend fuel and air. So therefore, in the reaction zone for non-premixed counterflow near extinction, the conditions is very similar to what happens at PSR. So that's why we derive the reduced model from PSR. It's always applied very well for counterflow extinction for non-premixed. But premixed is also similar. For premixed, basically you get twin flame, right? Fresh mixture comes in, but you get in the middle. So in the middle is the product. Okay, so when you try to use counterflow to blow the twin flame toward each other, they are approaching that. So near extinction, these two flames will merge. Their post flame zone will merge to form like almost a very, very thin stir reactor type of so-called combined post flame zone. Okay, so this region, it anchors the premixed flame at extinction. So when at extinction, this one will be similar to this condition. So extinction application is all the same. If you look at it locally, which point anchors the flame, and you look at the local equivalence ratio, and you look at the local temperature, and you translate to temperature, you translate to the PSR cases, you find they all collapse actually. If you look at Methodologies, you know, is the guy at UTRC previously. He was doing a lot of field research. He tried to map counterflow extinction cases to PSR. He found there indeed correlations. Many years ago, he figured this out. There's a kind of mapping between these two. And we are using his table how to map these two applications. Very interesting stuff. But the very different type of flames, they're the 1D, but eventually in terms of chemistry for fast burning, it's all the same. It's the same set of reactions, same set of species. Okay. So for a reduced model, if you want to sample from 1D flame, of course it's fine. But it's a lot more difficult to compute. It's a lot more time consuming. You need to march through the whole S curve for the 1D flame. And then if you use chemical 2, or even you use chemical 4, it's always painstaking. You know, sometimes it doesn't converge. If you get lucky, you can get S curve. But if you don't get lucky, you don't march to the turning point, and the program will diverge. So, but using stir reactor is a lot easier. Its computations are faster. Particularly if you're using huge chemistry, like if you use 3,000 species and 100,000 reactions, you just cannot compute 1D flame with this humongous detailed mechanism. So stir reactor actually, it does the job. It's fast computing, and also it gives you the important reaction states near extinction. So to help you to make sure the faster the burning rate is well captured. Okay, and that's the magic for using stir reactor. If somebody asks me what the best thing I did in my model reduction work in the last 20 years, I would say I included the PSR and the extinction of PSR in the model reduction. So that's the best thing I did. Okay. Of course, I can brag about a lot of math and computation method about other things. It's fun to do things, but something really, really important is to include the extinction turning point. It's really important. Okay. So next, I want to show you. Oh, another question? Yes.
Maybe this to confirm. So from Anurag, to compare reduced mechanisms to detailed ones, are 0D simulations like PSR and Autoignition enough, or 1D problems like flame speed and temperature and premixed frame are also useful?
That's another topic I will talk about a little bit later. But it's an excellent question. So it's a very, very, very important question. It's like it involves model validation. So why do we need to do validation? Because we want to make sure the reduced models work. You cannot validate your model in your turbulent flame simulation because you don't have a detailed model solution to compare with. And that's the point. So it's not practical to compare reduced model turbulent flame with detailed model turbulent flame. You don't have both solutions. So what you can do then? The only thing you can do is you do as much as you can. Okay. So if you find whatever flames which you can compute, and it's probably relevant to your turbulent flame, like locally, if you find some kind of flamelet or a local flame structure which resembles condition in your 0D or 1D flame, you probably want to do the validation. So it's never hurt to do more validation. But at least you need to validate the ignition delay time, because ignition delay time is absolutely mandatory. If you say my reduced model cannot predict ignition delay time, sometimes you can still use it, but people just it's not good, right? So if you cannot even predict ignition delay times, people don't think it's good. So but you can still find applications with totally wrong ignition delay time. You can still use it. For example, for jet engines. Okay, but usually we make sure ignition delay time is correct. Just to be proud. Okay, but sometimes we also validate PSR. So unless we actually don't care about fast burn. So although ignition delay time and PSR, we always do validation. But if you have a good method for reduction, you probably don't have to validate these two because you include them in the reduction already. So a good reduced model development procedure should make sure if you develop reduced model from these applications, it should at least be good for this application. So if your method is not even cannot guarantee this one, then probably you want to find some better method to use. Okay, so the method should at least guarantee if you develop your reduced model from PSR and Autoignition, you at least make sure your ignition delay time is correct and your extinction time is correct. In addition, sometimes we validate the flame speed, premixed flame speed, for different equilibrium on a different temperature, different initial temperatures. Non-premixed flame, so we do the whole S curve, including the extinction. Okay, premixed flame, we do extinction for twin flame. So that's pretty much the 5 sets of validation we do. If we want to develop some reduced model seriously for a lot of people to use, and we are not confident whether this model will certainly work for the turbulent flame, we want to do as much as possible. We do all the validation. That's why it takes about 2 weeks. So because ignition delay time and extinction don't need 2 weeks, it's 20 minutes down. So the S curve for counterflow extinction, it takes a lot of time. Sometimes if you do the detailed chemistry, it takes days or weeks to finish. So the validation typically, the time is spent on 1D flames. All right. I guess hopefully that answers this question. Yeah. Another question?
Yes. 2 questions just to clarify. So from Anurita, does NTC occur in the case of isoctane?
The low temperature chemistry is always there. It only matter whether it shows some important effect on your problem. So if for isooctane, NTC, the reactions are there, but it doesn't affect ignition delay time that much, but it bended a lot, but bended a little bit. So if you see the NTC for isooctane, it doesn't bend back. It's just there's some kind of bending in the slope. Here it's like this, here it's like this, but it just doesn't bend back. But it still has an effect there. Okay, so isooctane has a low temperature chemistry, but just doesn't show NTC here, but because it doesn't get negative, the slope. If you want to get a reduced model for isooctane, you do need to worry about the low temperature chemistry. So the different pathway control ignition delay time. All right, so for small molecules, you don't need to worry about the NTC or low temperature chemistry. So in this sense, we got two concepts, NTC effects and the low temperature chemistry. So if your engine involve a large hydrocarbon field at a lower temperature, whatever fuel you are dealing with, isoalkane or normal alkane, you both need to include low temperature chemistry there. Okay, but if you have small molecules like methane, sometimes even ethane, you probably can get away with only including the high temperature ignition chemistry there. So that's the difference. All right. Okay. Now the following two slides are something related to what we spent a lot of time to talk about the ignition versus extinction. Ignition delay time, if you think, are the big guys in combustion research community. Many of them are studying ignition chemistry. So ignition delay time, if you think Ron Hansen, the Hansen group, and a lot of Shakti groups and the chemistry group, rapid compression machine in universities, national labs, Jester reactor in Europe, and then we have flow reactors, right? Like if the Princeton flow reactors, Penn State flow reactor, all this wonderful equipment, this costly equipment, what they are using to measure ignition delay time. So pretty much to calibrate the time scale for radical pull build up. So it's very, very important. And absolutely, this is important for IC engine or compression ignition applications at least. So, so as a result, if you look at the detailed chemistry today developed by different groups, all the detailed chemistry before they are published all have been calibrated against experiment data. So there we can see plenty of ignition chemistry for popular fields. If you have a popular field, the chances you can find many sets of experimental data that you can calibrate your ignition chemistry. So to predict the ignition delay time, use reduced or ignition or reduced or detailed chemistry, it's typically not a big issue to choose who makes this detailed chemistry or which group it was from. Some people try to be picky about who makes the ignition chemistry. For ignition timing, it's all well calibrated. Okay, if it's not calibrated, it's not possible to be published. So that's for ignition study. Extinction is a totally different story. If you look at what happens for extinction, even for the smallest methane air, see, the extinction or fast burning chemistry can differ dramatically, even by order of magnitude. Even so, if you select the best mechanisms out there, for example, for methane, we have GR3, right? Yeah. Okay. We have GR3. Somehow we have, for example, Aramco mech, right? It's developed by the cost people, and FFCM by Haiwan's group. These are all the best mechanisms we can ever have. And if you put them together to compute for methane extinction, you find they give you very different. It's the same ignition delay time for methane, at least for high temperature cases. But for extinction case, extinction residence time, you find they can differ by almost order of magnitude. So the message here is for extinction chemistry or fast burning chemistry, we really don't have a lot of experimental data to calibrate our chemistry, although it's quite simple. The high temperature small molecule reactions are critical to fast burning, but it's poorly calibrated. And the reason is it's quite straightforward actually. Why? Because burning is too fast. If you imagine if you want to measure the extinction time or the fast burning time, the time if you look, it's frequently, this is link case. Okay, the link case is 4.5. But for stoichiometry case, a lot of cases, the extinction time is much shorter than ignition time. Ignition delay time, if you design engine, you know ignition time is measured in milliseconds. 1 millisecond, 10 milliseconds, sometimes even 100 milliseconds. Extinction time can be 2 to 3 orders of magnitude shorter. Frequently, it was measured in microseconds. So it's a lot more difficult to reasonably or accurately, reliably measure the extinction measurement time compared with ignition delay time. We think today all the well-developed equipment for combustion research are almost all for ignition delay study. Okay, for extinction we have counterflow extinction, whether it's premixed or non-premixed. But those extinction counterflow study, it's always kind of difficult to measure because at the extinction state, the flame is so thin. How to resolve this 100 micron or even 50 micron reactional structure? It's very, very challenging. You can't even just focus your laser beam to such a thin structure easily. Okay, so to have like a 10 micron laser beam or 1 micron laser beam even, it's very, very challenging. The time scale for the diagnostic, talking about a microsecond, it's just very challenging. As to control your reactor to burn near extinction without the flame jumping back and forth is not a challenge. So the whole business for studying extinction is it's another level of challenge to combustion study. And that's the reason why we don't understand extinction chemistry that better. The reactions we know which reactions, which species are important there, but we just don't have the experimental data to calibrate those reactions. And that's the what happens for now. Okay, you guys, maybe you can think of, if you want to design new experiments, new type of experiment to provide meaningful, reliably, accurately measured, fast burning limit for a reaction mechanism. So that can be very helpful to the like, for example, propulsion industry, okay? Rocket study, for jet engine study, even for defense, all these applications can be very, very useful. So that's something you want to keep in mind. But that said, for whatever detailed chemistry you have, whether you get a large uncertainty in it or not, so you want your reduced model to honestly to reproduce the extinction behavior of the detailed model. Okay, because but in terms of scientific research, we want to make sure our reduced model, I get to agree with that. We don't want to see, because we get large uncertainties for extinction for detailed model, then we can be sloppy for reduced model there. If you do that, your model probably will just give you other surprises. Okay, so and the thing is, we really don't need a lot of species reactions to make sure we can reproduce the extinction term. Okay, that's the story. And now I give you the secret for my research. I guess you can all do it much better than if you haven't done this before. So here is another some kind of stretch about this topic about extinction. It's because why extinction is important. If you think, if you get a turbulent flow, if you get a weakly turbulent flow, a lot of cases people say it's in the flameless regime. Right? If you get a flameless regime, that means the turbulent is not so strong to totally disturb the flame structure. You can pretty much do the tabulation for 1D flame structure and use it for turbulent flame simulation. And you can get away with even using a reduced model for reduced kinetic model for it. A lot of cases you can use flame library to quickly resolve the flameless regimes in turbulent cases, whether it's non-premixed or premixed. But what if you get a very highly turbulent flame, with, for example, premixed case? If you get a strongly turbulent flame case, we get this very famous Borg diagram. The Borg diagram, and basically you get two coordinates. One shows the turbulent intensity how fast the turbulent fluctuation is. The other is the integral length scale. It's like how much energy will the input from what length scale. So for turbulence, it determined if it follow this energy cascading curve, right? So the negative 5 over 3 is slow. So this one on the energy cascading plot here is where the energy of the input, so you get a length scale. And I got, so this one, the U prime or U prime squared or whatever, you call it turbulence energy. How much energy was here at what scale? This determines the remaining scope, okay, until it dissipates at the Kolmogorov scale. So this one, therefore, you put everything together. If you can determine these two parameters, in many cases, you can determine what happened to the turbulence. And therefore, people plot this one. For whatever condition you have, you can plot your cases on this map called a Borghi diagram. Okay, if you have a case here, so that means you pump a little bit energy to your flame. Okay, at whatever given length scale, and that's a weakly turbulent flame. In that case, your flame is just wrinkled. That's called a wrinkled flamelets. So you can get away with a flamelet library without even finite real chemistry here. Okay, but if you increase the turbulence mix, oh my goodness. Continue. All right, sorry, I got a phone call. All right, wait a second. Can you give me 1 second? I missed it. That's fine. So if my wife calls again, probably something urgent. If it doesn't call back, that's okay. Yeah, because my wife is picking up my daughter from the camp. Never mind. Okay, but if you have a lot of energy pumping out of this length scale, so what happens there? Your flame gets wrinkled, more wrinkled, and then eventually your flame gets broken into small pieces. That's called a broken reaction zone skin. If you get a very, very strong turbulence, your reaction zone even can be breaking into small pieces. That's called a broken reaction zone flame. So broken reaction zone flame is one of very important research topic in combustion. It's probably the least understood part. See what happens to the chemistry there. If you want to get a reduced model, how to predict it, like what the reduced model should at least be able to do, right? So if you only include autoignition delay time here, so you will certainly have trouble to predict broken reaction zones. But if you include PSR extinction, you can do a lot of things. Let me show you why, because I'll give you an example here next, which is a real endodecan flame simulated by DNS. Okay, DNS by my colleague Alexei Polanenko. So we had earlier collaboration to use DNS to simulate the premixed endodecan and air mixture coming from this side is a fresh air. Okay, this is a product. So you get this turbulent flame propagating upward to fresh mixture. And the turbulence is so strong, and you can clearly see the flame structure is breaking to very messy cases. So this is temperature plot. This is mass fraction for fuel, and this is mass fraction for intermediate formaldehyde and the intermediate species. So from all this plot, you can clearly see this flame it doesn't have a flameless structure at all. It's all broken into small pieces. And this colorless number is just 1,000. Let me see, 10,000, 1,000. It's 1,000. Okay, it's this one. So it's not terribly turbulent yet. You can get even stronger turbulence in rocket conditions. But this is like 1,000. Okay, it's capable to break this down. Then you want to see what happens in this flame. Is this a lot more complicated than regular 1D flame? And what chemistry do you need to predict it? So what happens is here, if this is the flame, we first plot the isosurface for the reaction front. So the red isosurface basically are the structure for the reaction front. If you want to define one, okay, you can see it's all messed up. So basically, this is broken reaction zones. There's no a layer of reaction zone. It's just everywhere. Yeah. And the second one we plot here, we plot so-called pockets. The pockets, you know, in a flame, if you have a flame, you have product here, you have a fresh reactant here. If this temperature is high, it's burned, right? This temperature is low, it's unburned. If you have turbulence, so for example, the microjet of turbulence, it wraps this up, flame, the flow pushes the flame around here, and then if another flow has jet here, it's like counterflow. What will happen is you get a twin flame here, right? Product, fresh mixture, product in the middle. Okay, product in the middle is all product. And then if you pinch at the root, so the flame can shed from here to form pocket, like there's a pocket of product in fresh mixture. And the local extinction, the local extinction here is necessary to pinch off a product pocket. And this product pocket, what will happen, it will be stretched next to different shape. And then you can pinch at a different location to make two pockets, like a smaller pocket here, smaller pockets here. And this process can go on and on until the product was just totally blended into fresh mixture. This extinction, therefore, is a process which can pick a glob of mixture from the bulk product and shed it to fresh mixture, quickly break into small pieces and mix all this heat and radical into fresh mixture. What you can imagine from this process, this so-called extinction process, is the big volume of product was mixed quickly into big volume of reactant and forced the reactant to ignite much faster than it could be by itself. Okay, because if a fresh mixture wants to ignite by itself, it needs to build a radical first. The radical build up takes much longer time. And then if you have product blending into the fresh mixture, you put both temperature and radical there. So it bypassed the ignition delay time for radical pool build up. So it just kick into the thermal runaway stage directly, you know. So you, in this sense, you can make ignition much faster. And this is probably the major reason why turbulent flame can burn so much faster than the laminar flames. So a lot of cases people find this burning rate for strongly turbulent flame just cannot be predicted by laminar flame theory. It's not like a reaction rate times flame surface area give you the burning rate. It's not the case. So this forced ignition through extinction process actually is probably one of the major things to drive the fast burning stuff. And this driving mechanism was from the extinction process. Okay, so a lot of things going up and down, except it's not a steady state, it's transient, but it goes up and down around the turning point for the S-curve. So you see the whole zone, the whole reaction zone, it's focused on this region near the extinction. So therefore you get a large volume of fast reaction in strongly turbulent flames. And that makes the flame so fast. And we figured this out, then it turned out the strongly turbulent flame actually it's pretty much controlled by fast burning chemistry. It's probably more relevant to PSR extinction than the autoignition delay time. Okay, therefore, if you have a sloppy ignition delay time model in your reduced model, you probably can get away with this. You can still predict like strongly turbulent flame correctly. Okay, and that's why you can probably get away with a small reduced model for strongly turbulent flame than even the weakly turbulent flames. Let me show you the movie here. I have to have the movie here. Let me see. Where did I put it? Here, let me go. Oh. No. Here's the movie, because I have the PDF file. The PDF file cannot play you the movie. But this one you can see, you pay attention to this blue pocket. It comes and break into small pieces. So when you see a big pocket of blue mixture coming up, that's the shedding from the bulk product of the surface. Okay, but after a while, the after a while, it once it pop up, it will be stretched and break down smaller piece. Eventually, the product just disappears. Okay, so therefore, the blue pockets is something that we found very interesting in strongly turbulent flames. It helps the flame propagation and burning a lot. And this scenario is very similar to the recirculation zone for, like, for example, if you get a jet engine combustion, you get a recirculation zone, right? Fast mixing to mix fresh mixture with product. And also for cavities, the stabilizer. If you get a fast, like a high-speed propulsion stuff, like a scramjet or whatever, if you get a stabilizer, flame stabilizer, in the recirculation zone cavity, you get similar scenarios as stir reactor. So, and you get a very strong turbulence there too. Okay, so that's the mechanism for flame stabilization. And I guess now we have the idea again. What's the important application you need to use for reaction state sample? We didn't talk about the methodologies yet, the reaction methodologies yet. I guess for sampling, we can wrap it up again. We know what IDT is for. Ignition is controlled by radical pool buildup, right? We know what for extinction. Extinction is important because it tells you how fast in the limit chemistry can burn. You want to capture that. And it's important for flame holding application and also for fast burner design. And the next, once we have all the applications ready, so we sample the reaction state. Suppose you get a reaction state with pressure, temperature, and speed concentrations. Then how do we get a reduced model? That's a little bit more technical next. Okay, so any questions before we go to the methodologies? Okay, so let's take a 5 minutes break. Okay, so because it's a good time, I guess, to take a break now. Hopefully, I didn't get you too exhausted yet. All right. Let's pause it. Oh, button for it here. Are you ready? Okay, so we're back, everybody. So I got 2 questions from the audience. The first question is, wouldn't the turbulence parameters affect the S-curve, and how is that captured in the function of residence time? So the turbulence parameters we're talking about is mostly about the energy cascading curve, right? So you all know this a lot of, when we talk about this energy cascading curve, there's a lot of things to argue about. So we all go back to this stuff. This energy cascading curve. Okay, so you have the integral length, and you have this u prime. Okay, so once you can u prime square, if you have this point determined, theoretically you can determine the rest part. Okay, because everything else is flow nature. So if you determine this point, entering point, everything else is fine. But actually, in reality, if you have combustion problems, the combustion can actually pump energy into your system from any different length scales, not only from integral length. But the stirring, if you get a fan, the fan can only pump energy in from the length scale of the fan. But if you get a combustion going on, the combustion can give you energy from any length scale. If you get a small spot, it can explode, give you like a small length scale input. But if you get a segment of flame, it bursts. If it can give you longer length scale. So combustion, there's no limitation what length scale it can pump energy into. So basically, combustion can give you energy from anything, anywhere. For example, it can be focused on here. A lot of cases, you can find this hump on this curve. A lot of people call this hump from combustion problems. For different flames, the hump location can be different. So what's the significance for this is it's like it messed up the whole energy cascading curve. So as a result, so theoretically for combustion problems, you can't determine turbulence with only 2 parameters. It just doesn't sound correct, okay? But we don't have a better way to do it. So far the LES of combustion still assume we are dealing with conventional turbulence. As long as you can determine 2 parameters, you can determine the flow. That's a big assumption for combustion problems. A lot of cases you find this approximation can be quite off. Okay, particularly for strongly turbulent flames, you will often find surprises. But that said, what happens to chemistry? To chemistry is local. Okay, if you get a local residence time, tiny small flame structure, because what happens over large structure, you can always break it down into local condition. What happens locally, whether you have fast mixing locally to put a fuel and hot product together, so that matters. So if you get a local spot, one side is fuel, one side is hot product, and it's quick mixing time scale roughly can determine where on the S curve this reaction is roughly located. So that's how you can look, basically map very complex flow field into the condition of a 0D reactor. It approximately locally is 0D. Assume locally whatever you find local mixing time, and then the local temperature and the equivalence ratio. You can always map it to the S curve to figure out roughly where it is. So as long as you capture the reaction condition there and the reaction pathway is there, your reduced model should be fine. Okay, if you get many different cases along the S curve, whatever, and then you can just you do a sampling along the entire S curve. So make sure it works everywhere, both on the upper branch and the middle branch. So in that case, it's safer. But again, you can never guarantee there's no new cases in turbulent flow. Okay, so so there can always be different mixing scenarios which you cannot sample from PSR, because PSR, you know the inlet condition, but local turbulence actually can mix intermediate states together. So that's a major difference from a complex flow field from a 0D reactor. So real flames, you can mix different intermediate states. It's like a stir reactor network. Okay, but if you only use a single reactor, you cannot exactly capture the reaction condition there, but hopefully the dominant reaction pathways are still there. As we said, the high temperature regimes are dominated by the same small group of species and reactions. And my experience is if you capture one or two or a few this limited conditions, you probably can extrapolate or use your reduced model in many other different applications, because it's all the same group of people playing the game at Extinction. Okay, hopefully this answers your question. Another question I have is, well, if you have two fuels, one is a pure component, one is a real fuel. They measure the Ceton number the same. Well, the question is whether you can, if you cannot find the experiment data for the pure component, can you just validate like because they have a similar ignition delay time, right? The Ceton number. Can you just use the other fuels experiment data to validate yours? Well, sometimes you can. Sometimes there can be surprises. So you know, the chemistry is very complex. If you absolutely cannot find an experiment data to help you, nobody can blame you for using the best you can find to validate your model. Okay, it's always, you can argue about this, just like getting reduced model. Nobody can guarantee you it always work. Okay, you just do your best and you can always argue based on that. Suppose you definitely cannot find any experiment data to validate your fuel, and then you can find something similar. You can arguably see this fuel should have similar property as that fuel. Then people will understand, okay? If in cases people later find this field indeed have different behaviors, and we all understand that can happen, okay? So therefore, don't be nervous. Just try it, but do your work. Make sure you cannot find any data. But if you can find some people do the experiment for this new field, so that'll probably be a better option, okay? So that's why we always need to have new experiments for shock tubes and flow reactors, and this equipments need to be run 24/7. Okay. All right. So I guess we need to move on to the next section about some technical stuff, how to do model development, derive skeletal model. So for the reduction method, I will be focusing on three different methods. One is called a skeletal reduction. So I'll be focusing on what we did in our group, okay? And timescale-based reduction, which is a big topic. Timescale-based reduction means something's fast, something's slow, and there's a lot of math to play. So over the last many decades, people have a lot of work on timescale-based reduction because the math is beautiful, okay? But skeletal reduction is, you don't have complicated math to play with. So what is skeletal reduction? It's to throw away somebody, right? If you get a group of 50 people, you don't want to carry all of them. You want to choose someone to throw away, right? Throw them under the bus or out of the bus. So who to choose to throw them, to kick them out? That's the question for skeletal reduction. It's just to find a subset of species, a subset of reactions to kick them out. And you want the remaining people to be happy, okay? For example, you retain the 20 species in the model. The 20 species should be correct when you do the simulation. Their concentration should be close to those from the detailed model. And that's basically what people usually target at, okay? So skeletal reduction. Now, so here is a very, very important logical question. I guess this is the most important question in skeletal reduction. It's not a methodology, not a math, not a logic, not a computing. It's a logical question. Okay, so I found this actually really bothering a lot of people, which is how do you throw away species? So the common practice is you find a method to measure how important a species is. So how do you know whether a species is important? So one way is you look at the reactions, associated reactions. You check all the reactions. You find one reaction is fast. Fast reaction has to be important because a lot of the stuff is going across this reaction. It's just like bridge. If many people go across a bridge, you don't want to tear it down, right? So that's the basic rule. You look at reaction rate. If the reaction rate is fast, this reaction has to be important. So that's common sense. And every reactant, every product involved, you have to keep them. Otherwise, the reaction will be not, it's problematic, right? You have missing component. So you have to keep all the species involving the reaction. So that's the one way. Or if you want to be more advanced, you want to look at something so-called sensitivity coefficient. So over decades, people do sensitivity analysis to study chemistry. Sensitivity, for example, if you want to study a target, you change the date time. You change the parameter for a reaction to see whether the reaction can change your target tolerably. Okay, if you see it has little effects on your target, probably this reaction is less concern. But if you find the reaction has a large sensitivity to ignition delay time, for example, you don't want to throw it away, right? Because you throw away some reaction with large sensitivity, you're in big trouble, right? So sensitivity analysis has been used to identify important reactions for a long time. In the literature, you can find people use, for example, reaction rate, sensitivity coefficient, sometimes global sensitivity analysis. You can do local sensitivity analysis, global sensitivity analysis. They're have similar usage, okay? And sometimes we use flux. Flux is more involved technique in terms it has a lot of species into the picture. Okay, you look at where the reaction starts from the field. So where the carbon goes, for example, it goes to this species, that species. If identify the major flow chart, like the path of the element flux or mass flux for different species, you find all the major route or the road where the element travel through. So you have to retain all the major branches or major roads. That makes sense, right? So therefore, flux analysis, people use this to plot those important reaction pathway. Remember, you have thick reaction pathway or thinner reaction pathway in combustion textbooks, and those are from flux analysis. You can have different variations of flux analysis because you can define flux to be carbon flux, H flux, or oxygen flux, or mass flux, or sometimes even other whatever defined flux. You can always define different quantity flux, but eventually you can always define the path with large flux, and you have to retain the path with large flux. Okay, so over decades, people developed the different methodologies for for finding important species using reaction rates, sensitivities, flux, and sometimes even more advanced, you find out the connectivity to see if somebody is linked to more neighbors, more species from whatever reactions. If somebody is involving 20 species, 20 other species, compared with somebody involving only one species, probably the guy more popular, it probably can be more important, right? So this is some kind of empirical, but it more or less makes sense. But whatever quantity you come up with, you can always discriminate against somebody, right? So if this quantity is large, it means this guy is important. If this guy is small, probably you can throw them away. So in the literature, you find what we have been doing as a community. Basically, we are throwing away those species. For example, it give you small coefficient, small sensitivity coefficient, small reaction rates. And if you look at the literature, actually, there are many methodologies. Let me go here first, okay? So sensitivity analysis. Sensitivity analysis is one of the most frequently used method. So whether it's local or global, so that's probably number one tool people are using in chemistry, whether it's compilation of detailed chemistry. Remember, in detailed chemistry, it's like a heavily reduced detailed chemistry. In compilation of detailed chemistry, including the reduction part, that's why you get the linear scaling. And then other reduction, detailed reduction, basically is look at the reaction rates. Okay, you have to keep the reactions, which is fast. Okay, principal component analysis is based on coupling. You couple this thing, you look at species group by group or reactions group by group. So again, you have to look at what quantity associated with this group. So somehow, if this group have a large flux or this group has whatever large quantity, you have to keep this by group. So there's a variation of whatever done before, and anything else. So CSP actually in the context of a skeletal reduction, it's not really about timescale analysis. CSP there's one CSP quantity, which is to compare normalized reaction rate. You normalize the reaction rate or normalize flux to compare which one is more important relatively to other. Okay, so it's all more or less comparing some quantity. So this is in the literature we have been using many of those. So somehow our experiences, and I have tried many of these methods in the early days, we get surprises. So we get surprises and actually the surprise sometimes it gives you very bad prediction. So what happens here? It takes me at least quite a long time to figure out what happens here. It's very simple logical issue actually. We are trying to construct a skeletal model by only keeping those important species that we identify. For example, those with large sensitivity coefficients. But the question is to develop a skeletal model, we are not to identify who must be important. We want to throw away those unimportant species. You know, a species with small sensitivity, it doesn't necessarily to be unimportant. For example, if you are dealing with a radical, it has very low concentration, okay? Its formation and the consumption rate can be rather slow compared with major species, which in high concentration. But you know radicals play a critical role in combustion to lower the activation energy. So its reaction rate was exponentially amplified through the Arrhenius term, through the lower activation energy. So this is not a fair comparison to just directly compare the reaction rate. But the reaction rate somehow has to be weighted by the exponential operation, okay? So if you simply compare their reaction rate, the radicals are being discriminated against. You tend to throw away some important radicals. That's why the reaction rates can be totally wrong if you only look at reaction rates, okay? So in early days, people figure out by only looking at reaction rates, only keeping the fast reactions doesn't work because you mess up those slow important pathways, okay? Some slow pathway can be important. Similarly, species with small sensitivity coefficient can also be important. For example, if you get a radical in steady state, and this, you know, in steady state, basically, its radical concentration is only function of some major species. It has very slow sensitivity to a lot of the other reactions or parameters or targets. Okay, so in that case, if you perturb this reaction by 10% or 20%, you don't find it's actually an issue. For example, if you get a formation of a radical with rate 1, but it can be consumed very, very quickly, a factor of 1,000 faster. But the thing is, if you perturb this reaction by 10%, it actually doesn't matter at all, because this reaction is choked by the inlet. Okay, but if you cut it, that's a different story. If you cut this insensitive pathway, the radicals have nowhere to go, and it will accumulate. Its concentration will be wrong, and your reaction will be totally wrong. Okay, so that's why reactions with low sensitivity sometimes can be important. And if you throw them away, you can be in big trouble. So logically, what we have, the problem we have here is if we only keep those species or reactions with high sensitivity or involving fast reactions, we are risking throwing away some important species or reactions has lower sensitivities, because some important species can have low reaction rate, have a low sensitivity, low whatever quantity you come up with. Okay, that's a major problem. It's kind of hard to believe over decades. This kind of very simple logic is bothering us for this long. But what happens here is then we try to think of whether we can come up with a different way to directly identify the so-called unimportant species. Can we define some quantity to measure the unimportance for a species? You know, it's easy to measure importance for a species, like a sensitivity indicates the importance for a species. But our objective is identify the unimportance for a species, right? Because you want to throw away unimportant species. It's kind of, this. I hope you got the logic here. So the tricky thing is not to identify who is important. It is to identify who is unimportant. And one of the working methods to identify who is unimportant is to use errors. If you get rid of somebody, to see how much error it can induce to the other people or to a target. So if you define or unimportant to be error, so see how this works. That's what we did in the DRG method. So based on graph theory, the direct relation graph, something here. Okay, we define like locally so-called pairwise importance. So for example, if we get rid of one species from the mechanism, somebody will be affected, right? Who will be affected? Anybody involving a reaction, they appear together will be affected. For example, if A plus B go to product, if you get rid of B, this reaction needs to be gone. Okay, you cannot keep the reaction if B is eliminated. So therefore, this reaction will be eliminated, and then A reaction rate will be affected. In that case, if we throw away species B, now we can define an error, relative error. How much B can induce? How much error by eliminating B can induce to A? We call this RAB. So there are different versions of definition, but the flavor is the same. Okay, on the bottom is all the reactions involving species A. For example, there are 100 reactions involving species A. They all have the same reaction rates, let's say, but only 20 of them involving species B. So about 20% error will be induced to this one. Okay, but if the reactions have different reaction rate, you take the reaction rate into the picture. So basically, you put them, sum them up, or you pick the maximum one. You define whatever reasonable or relatively reasonable error. Okay, this has to be an error. So basically, you throw away B. How much error it can induce to species A? And if this error is small, we can know B is not important to A. So this is some good definition for unimportance. If you think this way, we don't actually have a lot of candidates how you can define unimportance for a species, right? That's a rather tricky question. So sensitivity defines the importance. Reaction rates define importance, but errors indeed tell you unimportant. Okay, so that's why we use the graph theory. And the heart for graph theory is not the graph, it is how you define error and to use error to throw away species. You don't have to use graph theory, but as long as you look at the errors, you can do a much better job than using sensitivity coefficients just for reduction in many cases. Okay, that's a little trick. And the graph part is to make it more, seemingly to be more professional or more advanced. But the story here is very simple. Once you identify those pairwise errors, if B is important to A, or if you throw away B, it can induce some kind of a large error to A, B is important to A, right? So we use arrow. So we put all the pairwise arrows together. For example, you get A, B, C, D, E, F in this graph, you get 6 different species. So for example, if A is important if B is important to A, we use arrow, say A requires B. So this arrow means a requirement. That means if you want to keep A in the skeletal model, you have to keep everybody important to him, right? So therefore you need to keep B also. And if you want to keep B here, who else you want to keep? So everybody important to B, you need to keep it there. So that's a simple logic question. And then you search the arrows. Oh, B can go to D, right? You need to, from A, you need to keep B. B, you need to keep D. And D, where can you go? D can go back to B, then the loop is closed. And then D require nobody else, nobody else. So therefore, this way, you identify A, B, D, the 3 species, which is sufficient to predict A. So if A is your interest, we call it a starting species. So for example, it's your fuel or your product. You start from A, you find everybody it can reach, or everybody it requires, whether it's directly or indirectly. So this way we can find everybody A requires. And if A requires B, we find also everybody B requires. So until this picture is closed. And this graph searching method is called the depth first search. If you study computing theory, you know DFS is like the most rudiment or most elementary methodology you can ever find for graph theory, right? It's really nothing profound. And the way how do you search graph? It's just like a little hamster. If you have a little hamster, it goes through a maze. It finds all the doors one by one. The depth first is something like the hamster going through all the possible doors. Okay, but you get it. You get the flavor. So basically, the DRG or the graph method is rather simple. The key is to define a reasonable error, and this definition is not unique. You can use this definition, and we come up with a different definition, like a summation, for example, rather than max. So arguably, the summation can have some limitation if you get many reactions. But this one max, we find out this particular definition works the best in my experience, and then we stick with this almost all the time. So this is basically this definition we find it works really well. Okay, for almost all the applications. But then you can also come up with your own definition. So is there always variations? It doesn't matter too much. So as long as the definition is correct, it can measure it's reasonable to measure the actual error. Then it's fine. Okay, so then we use DRG to. The good thing for DRG is you can see everything is simple, right? Everything is simple. The definition for errors is simple, and the graph search is simple. All this methodology can be applied very, very fast, actually. So the DRG method can be applied in a blink of eye to reduce a huge mechanism to half, or sometimes even a third of its size. So it's very useful to reduce larger mechanisms. So we apply for many things. For example, this biodiesel mechanism, it has more than 3,000 species starting. And then we can quickly run DRG and chop, like with about a 20% error or 10% error, it's chop it by about a third, okay? And after running once, if you're not happy, you can run again until you cannot remove anything anymore. So we call it a multi-stage DRG reduction. The first stage, second stage, third stage. So after the third stage, you find you run more. It doesn't matter too much. So you just stay here. You start. So eventually, you just choose to have like a 1,000 species skeletal model. So that's the product from DRG. So everything is straightforward. Okay, the graph theory is nothing profound, nothing profound. The essence is logic here. So how to define unimportance for species. If you use importance, you run into trouble. You won't find it. If you use unimportance, the chance is you find it. The chance of running into trouble is much lower. So okay, but again, you cannot guarantee it 100% work in all different cases still. So sometimes you get a slightly larger error, a smaller error, but that's all the secondary effects. Okay, that's how DRG works. And so because we use graph theory, and also the method is very simple, you can see based on this graph here, we plot how much time it takes to reduce one reaction state from the sample space, okay, versus how many species you have here. And you can clearly see that there's a linear trend, because all the method we use here, all the operations, even the computation of the error, and also the graph search, every step, it can be achieved through the so-called linear time. So in computing theory, linear time is the best you want to do. Because if you want to develop an efficient algorithm, if the cost in linear proportional to the number of variables, that's typically not a concern if you have huge n, 1,000, 10,000. Typically, it's not a big problem. If it becomes a quadratic function, it's a lot more time consuming, because when you get a 1,000 species, if you time another 1,000, it can be costly. Okay, so any quadratic algorithm will be time consuming when you run them for larger mechanisms. In this sense, when you select your toolbox to deal with a large mechanism, try to select something very efficient, okay, and try to select something which you can trust the best. Don't be very aggressive in this stage. You cut the size by half, and you work with half-sized mechanism. It's a lot faster, because many simulations can run not by a factor of 2. If you cut a factor of 2, your simulation can be a cubic function. For example, if you run flame speed calculation, you find that the computation time is a cubic function of n. If you half the size of the mechanism, your simulation can be 10 times faster almost, okay, a lot faster. So don't be too aggressive in the first reduction stage. After the first stage, you can roughly check whether everything makes sense, and then you go to the second stage to use more complex or more time-consuming method. The target is to minimize the size of the mechanism in the following stages, okay? But not the first stage. The first stage, try not to be too aggressive, because you're beating yourself too much, because it takes a lot of computational time, okay? And another feature for DRG is reduction error. Statistically, it's a linear function of the error tolerance you specify. So basically, we can specify we want 10% error. The chances you'll get 10% error in most cases. So they're a little bit scattered. You see, you can never guarantee anything for nonlinear cases, but statistically, it works really well. Okay, you want like error to be 10 to the -3. You roughly get this worst case error. This is not the mean error or this. You can see the worst case error is roughly bounded by this line. So about 1 order of magnitude than your tolerance. So you specify your tolerance to be 0.01. Your error tends to be 0.1. So that's roughly our experience for DRG. Okay, I get a question here. Okay, Francesco Guzman. When looking at a detailed mechanism, some of the rate constants are often based on educated guesses and not necessarily experimental data or high-level ab initio calculation. Can the mechanism reduction process reduce the error in rate constant compared to a detailed mechanism? This is an excellent question. When you compile detailed chemistry, there are a lot of guesses in determining the reaction rate. Actually, my opinion, okay, is you get thousands or tens of thousands of knobs in your detailed chemistry. You turn any of the knobs, you can change the prediction. So, and how to turn the knobs, people typically can do sensitivity analysis. You perturb some knob to see whether you can change some initial delay time, right? And then you choose 10, 20 different parameters or 10, 20 knobs to turn to fit the initial delay time. That's typically how the rate parameter was calibrated against experimental measurements. There's a lot of issues about this kind of knob turning stuff, and I will discuss in better detail in the fourth part of the model reduction about tuning. So although I will focus on the tuning for reduced model, but then also the same thing applies for detailed model. If you get too many rate parameters to tune, so first of all, you can easily fit any target you select because you have so many models, so many knobs. Okay, you get a million knobs to turn, you can fit the whole thing in the universe maybe. Okay, not to see a initial delay time or a set of initial delay time. But if you want to fit the initial delay time together with some flame speed, keep in mind those data sets are not independent. Okay, so it's like you get 100 set of initial delay time. Some of them are redundant. So that means you turn one knob, maybe all of them will become better. So you don't really need to turn a lot of knobs to make a detailed model to fit initial delay time. That's why, as I said, you look at a different detailed models, their initial delay time always work well because they are calibrated. Okay, and that said, so this detailed model work equally well for uncalibrated target. For example, extinction time. No. Okay, the answer, short answer is no. We know the extinction has surprises even with the best detailed model we have today. So and there's really not much you can do with it. So so we can just do our best for guessing these parameters, and there's no way you can tune it to remove the uncertainty. Mathematically, it's not possible just to turn the knobs to get rid of the uncertainty. The knob turning is to hide those uncertainties, but not to remove them. It will show up somewhere else. Okay, and the reduced model, there's no way you can get rid of those uncertainties. If you get rid of those reactions, you are getting rid of those reactions, but you still have a lot of knobs there. For example, if you get a factor of 10 uncertainty in some important reaction pathway, it will show itself when you are dealing with the right target. Okay, so in my opinion, the model reduction is not really to remove uncertainties in the detailed model, and it cannot actually. It can reduce the model complexity to give you fewer knobs to turn. Okay, and it can give you similar prediction to the target function, but it shouldn't be able to remove the major or important uncertainty in the parameters. So I hope this answers your question, but this may or may not be correct. Okay, we can always discuss this if you're interested. Another question I have is during DRG, we identify the unimportant species and eliminate all reactions associated with unimportant species. After this process, is it possible that some unimportant reactions remain in the skeletal mechanism because it contains all important species? Yes, this is an excellent question. I didn't mention here because the DRG is to only throw away safely throw away those unimportant species we identified. So first of all, there could be some unimportant species we didn't identify because, as we said, some species can give you slightly larger errors than tolerance, but you finally throw it away, it's still fine. It happens sometimes because error can cancel with each other. Due to the nonlinear propagation effects, that's involved the next component here is so-called error propagation model. People try to see how the error after a few steps, how it can actually affect your target. So based on DRG, we are assuming this error from A to B, for example, it can propagate in many steps to another species without decaying. Okay, this is a kind of strong assumption, but it's on the safe side. So we are trying to overestimate the error one guy can induce to somebody far away. Due to this kind of overestimation, we will talk a little bit more detail next. So you can have some kind of unimportant species in the skeletal model from DRG. And that's why you need to do further reduction. You want to the next stage of reduction. But the important thing is you want to be safe in the first stage to quickly remove some unimportant species, not all of them, okay? To safely remove and to efficiently remove. So that's targeted for DRG. And also there can be unimportant reactions retained. So even though you remove all the unimportant species, there can still be unimportant reactions because there can be reactions involving important species, but the reaction itself is not important. So elimination for unimportant reaction actually is a little bit easier because you just compare how much effect this reaction has to every species. That's what we call the CSP criteria. Remember in skeletal reaction, we have CSP criteria. It's to look at how much effect this reaction has to every species. If this reaction doesn't matter to every species, you can throw it away. And that's what I mentioned in the previous slide about using CSP, something called the importance index for a reaction to remove an unimportant reaction to everybody. Okay, but it's not a job for DRG. DRG only focuses on removing species. So we handle reaction elimination in the next step. Okay, so wonderful questions. I'm really happy about having all these questions here. And there, after DRG, this one thing I didn't mention is DRG is somehow become very popular, very popular. To my surprise, has become a popular method. If you look at citations, it's cited by a lot of people. But I was a little bit surprised because this is really a very, very simple method. But the simple method actually, it works quite well. It's just like if you want to make a tool, if you want to make a very, very simple tool, for example, a screwdriver, it can be very simple, not very complicated, but it's very useful for a lot of stuff. Actually, this kind of tool can be very useful. So that's a good lesson I learned. It's quite interesting. Sometimes you find your contribution to the community is not just kind of things with very fancy mathematics, derivations, or theories, or computational method. So I have something else which I think I feel a lot more proud of. But somehow, maybe it's too complicated. The method, for example, how to identify quasi-steady-state species, it involves a lot of linear algebra. And maybe it's too complicated and scare people away. But I just never expected DRG, such a simple stuff. So simple concept can be that widely accepted. So the lesson here is, if you want to build something, sometimes simple stuff can really work well. So we don't really have to beat ourselves to use very fancy or advanced math, whatever. Okay. Okay. Oh, it goes away again. Let me see. Which one? Here. Okay. Okay. So let's move on to talk about the other method related to DRG. So the other method, so there are quite a few methods developed after DRG. So more or less, we call it graph-based method or connectivity-based method because we study of the relationship between each pair of the species, and then we map the thing to a graph. Sometimes people call it network. If you look at in the recent paper called the Between centrality method, which is similar to what Twitter used for social network, it also mapped this into a network or to a graph. You call it a graph. And the kinetic-based method basically takes everybody to a picture and use some kind of computing method, try to identify a subset of important species or skeletal species. So if you look at this species of these different methods, one of the major difference here is how to define the error. This very, very simple stuff. the other things are actually relatively minor. For example, how to use thirst graph. Some people use depth first. Some people use breadth first. It's like you visit this door first or that door first. It really actually doesn't matter that much, because eventually, as long as you can go through all the doors, you find all the same thing, right? Actually, the major difference all lies in how do you define unimportance? How do you define unimportance? If you want to be a little bit more aggressive to define it, you probably consider, for example, in DRGEP, the DRGEP theory, it says if error induced here, after, like for example, if you have species induce the error to this guy, okay, and this guy after many steps it can affect somebody else. The DRGEP assumes error can decay along the graph. For example, if you go through 10 steps along the graph, so probably the effect on the last guy will be less compared with the effect on the second guy. That's totally reasonable, right? It sounds reasonable. So therefore, in DRGEP actually, it uses the so-called the geometric decay theory. For example, if the error here is 0.1, this error is 0.2. So this guy's error to the third guy is defined to be 0.1 times 0.2, with whatever weighting factor or scaling. So, but the key idea is the error can decay geometrically with more steps, so the error becomes less and less important. So this is a little bit more aggressive way to define error, but it works for a lot of cases. Actually, it helps you to eliminate more species. Okay, but just later I will show you something like a. But if you want to be too aggressive, sometimes you can underestimate the error. For example, this guy's effect of this one, after many steps, it tends to go to zero, right? It decays several times, it tends to go zero. But actually, due to some nonlinear effect, it may be 0.05. Let's see, it can happen. Anything can happen on linear work, right? So that's why for nonlinear problem, you want to be more conservative to overestimate the error. But if you underestimate error, so basically you can, if the error here you find is zero, you find this guy is not important to it, you can probably throw this away. But in reality, if you consider nonlinearity, this may be important to the far right people. Okay, so in this case, you induce some kind of risk in species elimination. So if you compare the skeletal model from DRG and DRGEP, DRG give you larger reduced model with same error tolerance. DRGEP give you a smaller one. Sometimes you find a smaller one give you more error than you expected. But that's not the end of the world. What you can do is you can go back to use a different error tolerance and to use a smaller error tolerance. So you try a few times and you can determine a working error tolerance and give you a working model. So as we said before, no matter what method you use, as long as your reduced model can pass validation, it's fine. Okay. The only thing that matters is how much effort you need to put in, how many iterations you need to do to eventually get a working reduced model. Okay, so that really matters for a method of scalar reduction. The scalar reduction is really nothing profound, actually. So what I found is we probably shouldn't assess like the rigorosity for any method for scalar reduction anymore. So probably if we do a computation with different method, we should compare who is more efficient or to obtain a reduced model. Okay, I guess that's probably a more fair comparison. Okay, so that's about the DRG. Yeah, here is the graph. Somehow I just let's just skip this one. So another model we extended from this definition for error as unimportant for species is, DRG it assumes error does not decay, and DRGEP assumes error geometrically decay, right? So one is probably too conservative, one is a little bit too aggressive. So can we find something in between which give you a little bit better measurement for the error? And that's what we did for this linearized error propagation. Okay, so for small errors, if you get small errors, you can probably estimate the error propagation with a linearized model. But anything small can be linearized. So that's how the math or linear algebra comes to play. And that's the little toy we developed. So Yun Chao came up with this LEP method. This method uses only PSR. And we said PSR has 2 turning points. This one is for fast chemistry, okay? This one for ignition chemistry. So therefore, if you include both extinction and ignition turning, somewhere here, you can capture both ignition delay time correctly and the fast burning correctly. So, so the little secret here is that you actually don't have to include both autoignition delay, autoignition and PSR. You can also get away with only using PSR, but you need to include the lower turning point, okay, in the sampling, so which is relevant to ignition problems. So PSR to be convenient, so we just use LEP, the linearized error propagation method. We use PSR only because the formulation is simpler. You don't want to derive different set of formulations for different applications. So we use LEP, but then we included both the extinction and the ignition in the sampling. So hopefully we can get similar comprehensive model as what we do by using both autoignition and PSR. Okay, so then what we do is we use PSR. We sample many points. For each point, we linearize error. Okay, so we do a model reduction at each point, and then we join all the models along the S-curve to find the maximum, or we call the uni for the species set, to which will take care of everybody. How do you do the linearization? This formulation is actually quite simple. What you do is you just decompose the reaction source term into 2 parts. One is involving the retained species. So in this method, we get rid of 1 species at a single time. Okay, if this species doesn't cause any trouble, we can throw it away. If it causes any trouble, we have to keep it. So therefore, each time LEP just deletes 1 species. And if it deletes species, this guy is the concentration for the species, okay? And this reaction involves the eliminated species eliminated reaction involving the species. So therefore, this is the deleted part, both the source term and the variable, okay? And this part was the retained part. So therefore, you want to figure out how much whatever other quantity is sensitive to the elimination for the guy. If you get rid of some species, how much error it can cause to everybody else, like the concentration, temperature, and all the solution. Okay, so eventually we can derive, because it's linearized. So you can easily use the Jacobian to derive this, and then what you come to do is you can define error. This error is a much better estimation considering this kind of error propagation, but from linearized theory. Okay, you measure how much concentration was changed in A because you change from YA to 0, right? This is basically how much error you gave, and then let me see this. Yeah, on the bottom basically it's normalizing factor to make it a percentage. Okay, so this way it measures the relative error it can induce to everybody else just by eliminating 1 species, and you can use this definition to replace what happens in DRG. But rather you don't need to do the graph searching anymore, because you already know whether it's directly or indirectly. If you get rid of species B, how much error it can cause to everybody else. Okay, you just get rid of B if it doesn't bother everybody. Okay, that's the simple story about LEP. So you assume the errors are small. The concentration of eliminated species are small. So therefore, you don't try to eliminate any major species. You only eliminate species with very low concentrations. But if you try radical, you find it can cause a larger error to others. If you try some low concentration species, which is not important, you find it doesn't bother anybody, then you can throw it away. So this can be formalized like routinely done by LEP. But error has to be small for this error to be reasonably well estimated. So if you compare what happens to DRG and LEP and DRG EP, you will find so these are errors estimated from DRG. So it's measured. If we find a pair of species A to B, for example, okay, if you get rid of B, you specify 10% error, but actually you measure the error can be much smaller than your tolerance. That's typical in DRG because you overestimate the error. Okay, let me see. In DRG EP, it's interestingly you see DRG EP. If you specify 10% error, you may get a larger error. So that's why in DRG EP you find that if you read the paper, typically you specify a much smaller error tolerance. For example, 0.01, and there's a factor of 10 roughly difference. You have if you specify 1% error tolerance, you probably get 10% error. So statistically, you get this trend. So the green circle that was from DRG EP, and this worst case error is basically about 1 order of magnitude higher than your error tolerance. Okay, so that's why if you look at the papers, if people use DRG, they specify 10% error. If people use DRG EP, typically they specify 1% error, the tolerance. Okay, but eventually you get a similar sized reduced model. Okay, so that's a little thing. But if you look at the LEP is dead on at the center. So that means for small errors, like particularly this portion, because everything is smaller than 0.01, it's considered small error. Okay, it's dead on. Basically, because small errors are indeed linear problems. So it's almost exact. Okay, so LEP therefore, it's very good to actually capture small error propagation. You don't need to model this one for small error. But when it goes to larger errors, nobody works well all the time. So sometimes because you get it. Some people say 30% error tolerance. So what will be the resulting model? Anything can happen with 30% error because it's not a small number anymore. So but that's life. A lot of people just want to be more and more aggressive because we want to get a smaller reduced model. Right? How do you get a smaller reduced model? We want to specify higher error tolerance, 30%. How about 40%? How about 50%? A lot of cases people like to try 50% error. But if you think 50%, if you inverse it, it becomes factor of 2. Okay? If you see 50%, a lot of people think it's fine. If you see factor of 2, most people will see not good. But 50% error is the same as factor of 2, what I can tell you. Okay, so just don't be too aggressive because we are dealing with really tough problems. This nonlinear chemistry is a really tough problem. You don't want to be too aggressive to it. So and so particularly if the risk is too costly, if you run for example, if you run a big simulation costs you 10 million CPU hours, 20 million CPU hours, you don't want to risk like 50% chance to get a totally wrong result, right? So it makes a lot of sense to balance, to find a balance point of like how safe the model is versus how much it will cost you. You do need to get some experience to be good at this kind of balancing. But again, nobody can really criticize you too harshly about making errors here. Okay, and the graph-based method also, they are good for making something called on-the-fly reduction, or some people in the literature will call it dynamic adaptive chemistry, DAC. So the whole idea here is typically we get a static reduced chemistry, reduced model. We do the reduced model beforehand, and then we use the reduced model on the fly. I mean, we reduce model in the large simulation, so we don't change it like during the simulation. But the interesting idea for DAC is, what if we use reduction on the fly? So why sometimes you prefer to do the model on the fly? Because for flames, you get different zones, right? For example, this is a lifted jet flame. Lifted jet flame, you have fuel injection to hot air. It's hot air, and then you get a mixing layer which have a reaction flames going on. So this is temperature plot. And most reactions occur only in a small layer of reaction zone, or nearly the reaction zone. So if you think in the air side, on the air side here, or in the jet core where 300 Kelvin temperature is very low, reaction is not going on there. Right? You don't need a complicated chemistry to capture what happens in pure air. So the benefit for on-the-fly reduction is basically for different zones, you can get a different chemistry. For air, you can get the 3 species without reaction. It's fine. For jet core, you have fuel and then dilution, and probably a little bit of the major species. You can get away with it. You only need larger reduced model near the mixing layer, right? So where reaction actually happens. So if you look at how many species are needed at different zones, so basically this tells you the number of species, typically between 15 and 20. So that's what you need to predict the worst case scenario for ethylene. This is ethylene flame, okay? You pretty much don't need anything on the air side. Very few in the jet core, but mostly it happens in the reaction zone. So this is a 15 or 20 species needed for the layer. For DSC, on the fly reduction, arguably you pay the cost on the fly for the reduction, but then you can get a smaller reduced model in some of the flame zones. So hopefully for some kind of well-designed DSC algorithm, you can benefit overall, okay, in the simulation. So DSC basically, the requirement is, first of all, if you want to choose a method for DSC, you don't want the method to be too costly, too expensive, right? DRG is a perfect candidate, or DRG-EP, graph-based method, as long as linear time, you don't have a lot of overhead for the reduction. Then you can apply on the fly with a little overhead, and then you don't need to run a lot of validation. So if you have a safe method, you can avoid doing a lot of local validation, okay? But again, you can never 100% guarantee your local model always work. But that's the best we can do. Okay. In most cases, you get a local reduced model and it works reasonable well. Okay, in most cases. Sometimes if you get a surprise, we go back to look at what happens there. So we can always iterate and fix problems. Okay, so I get 5 minutes left. Let me finish this part, skeletal part. But one thing in DAC, the most important thing for DAC is, again, a very simple logical problem or philosophical problem. People tend to ignore this problem. It's like, DAC is to throw away species for them or reaction right now, okay? But then in the flow field, in the future time, if somebody is thrown away, it's no longer there for some time. There is a possibility that some guy is like not important right now, but it's becoming important in the future, okay? But if you throw away right now, it doesn't have the chance to become important again. So the logic here for DSA is the important or unimportant species, even though you can identify all the unimportant species right now at the current time, you cannot guarantee it never become important in the future. So unimportant species right now may be important in the future. So that's the logical issue in DAC. You need to keep in mind, right? Logically, there's a possibility that you throw away something you think is not important to the flame, but then you change the future. Okay, so that's something you need to keep in mind. So if you are working on DAC, you can probably try to figure out a solution of this, and maybe it can benefit humankind also. It has a lot of common issues with many other things. I guess so after skeletal reduction, then we next stage we can apply many different methods. Right? Here, one method we apply is so-called sensitivity. So sensitivity method is really straightforward. We don't want to spend too much time on this. I can finish in 1 minute. So sensitivity basically, this sensitivity here, I'm talking about global sensitivity. Or in other words, it's called a validation. You can call global sensitivity to be validation. Okay, what it means, you throw away something, you see whether it affects your ignition time, flame speed, or whatever you're trying to calculate. Okay, that's called a global sensitivity. Well, the global sensitivity is basically you try it in the real thing to see if it works. If it works, you accept the model. If it doesn't work, you don't accept. The major things for global sensitivity, if it tells you work, it works, okay? But the bad thing is it takes a lot of time because it's very, very time consuming. You want to save time for global sensitivity. How do you save time? The little trick here is, you know, the field is almost always important, right? The field is almost always important. You don't want to throw away field. And the oxidizer is always important. You don't want to throw away, you don't want to try to throw away those important things. But can we have some method to identify more species we don't want to even try at all? So who we want to identify? In this case, you can identify the important species. The important species, importance becomes important. You can use sensitivity. You can use DRG. We have this error. You can use error. Large error probably means important. Okay, if its error is too large, absolutely important. So you come up with something to measure the importance between the pair of species. Okay, so in that case, so you exclude a subset of species from the test of global sensitivity, and it can save you a lot of time. So that's a little trick here. So using DRG information to identify this set we want to exclude from global sensitivity, that is called a DRG-aided global sensitivity. And that's the whole story, okay? And by the way, global sensitivity, we always use that the last step for obvious reasons, because you want to use it for smallest candidates, right? So anything more time consuming, you can really afford it. And basically DRG ASA, it takes days or weeks to finish. So in our cases, and after the sensitivity is done, your validation is done, basically. Yeah, so I guess today we just finish here. It's good timing. We have one question. So in DAC method, when the species is eliminated, where is mass of eliminated species added to? Oh, that's an excellent question. I found we get a lot of expert in the audience. It's very exciting. If you get rid of one species, the common method to treat it is that you treat all the species there in the transport equation, but you just frozen the reaction source term for those species. Obviously, it's not the best treatment. But if you throw away the species from the transport equation, you need to deal with the conservation law issue. Okay, sometimes messing up conservation law is not it's not pleasant. It can have surprise to you. Right now, whatever I can see is they keep all the species there. So you still need to do more or less a static reduction. But for the remaining, you keep all the species, and then on the fly, if you find species not important, you only freeze its reaction source term. Every other term you still carry it. So this way you still have benefit in computation cost, because once you get rid of the reaction source term, those terms will not give you stiffness. You can solve those species separately with different method. It can be programmable to make it more efficient. Okay, so thank you for the questions. Other questions? Otherwise, we're all done for today. And then I guess this one also answered, right? Yeah, the first one. If there's no more questions, I guess wish everybody a happy evening or morning. It's very exciting to have audience from all over the world. Thank you for listening. Okay, and see you tomorrow.